Do you want
Yeah,
longer?
I got go. Wait till 3 and start. Wait till 3 and start.
Okay.
That's it.
Gentlemen.
That's it.
Hello, everyone. So first of all, thank you for coming and spending your first session of the day with us. We appreciate it. And we're going to be talking about pipelines. My name is Chris. I'm the Chief of Product at ICVR here.
I'm Ihar. I'm CEO of ICVR.
And before we get started, just for reference, I'm curious, how many of you are game developers out there, if you can raise your hand? OK, minimal game developers. What about linear content? Who makes linear content? OK. Fortunately for you, we are going to be talking about pipeline in the context of linear content here. But all of the things we're talking about are also going to be very relevant to game dev, in-camera VFX, and really any usage of Unreal Engine where you're creating assets externally for it. The more assets, the more important pipeline is going to be. And what we want to do here is kind of share what we've been working on with our licensed pipeline tools. And we hope that's going to be helpful for people that are looking for a pipeline solution or people that are building their own pipeline and looking to expand it further. And what we want to do is call out some specific tools and automations that we think are high impact throughout the process. And we also want to touch on some Unreal workflow methodologies that we believe in for efficiency.
So Chris and I, we founded ICVR back in 2016, coming from game studios. And initially, we started with a focus on immersive entertainment. We built VR experiences. And through past years, we grew our studio into three divisions. We have IC Studio, which is focused on primarily game development and all sorts of work for AA and AAA game studios. We have ICVR, which focuses primarily on immersive live experiences and location-based experiences, and also through the past 5 years, been doing a lot of in-camera VFX, visual effects, and animation using Unreal Engine. And IC Tools, our division, which we launched in about 2020, which focuses primarily building tooling and pipelines for game development and animation. And through the past years, we're grateful to have been working with many top studios across board, from game development to linear media. And we're grateful for our partners to support us. And thank you for Epic Games to having us here. And so from our perspective, what does pipeline do? It's, the main part is we want to have our artists focused on creating art. And without pipeline and tools focused for the artist and engineering workflows, we see that we spend about a third of time on logistics, like submitting files to Perforce, like creating files, creating folder structures, naming conventions, like updating tasks, et cetera, So we kind of like break down our optimizations into three main points where like we want to be able to track task statuses and hands-off between each artist easily, eliminate repetitive tasks as much as possible using automation, and limit as well the possible areas of errors. Because then it creates additional iterations and kind of back. And the last but not least, it's track the assets and make sure nothing gets lost across the production. Because projects getting bigger, the environment getting bigger, and each environment can easily be constituted of hundreds of assets. And overall, our pipeline goal is to create efficiency as production. And here's like a quick example, why do we need pipeline? So to create this environment, we, even though it was environment it's out of Unreal, and we used a lot of existing Unreal tools like Quixel Megascans and Brushify, like in terrain builders, lighting in Unreal, etc. But we still have to use a lot of external DCCs, like, for example, the walls were created in Houdini and procedure generated. The texturing was done in combination of Substance Painter and Photoshop. The decals were created in Photoshop and Substance Painter, like wooden beams, and a lot of modeling been done in combination of Blender and Maya. And so all of these files need to be tracked, all of the tasks need to be passed off easily between each artist, and also we need to know where these files go and what happened in that. And because without that, the production can go into chaos.
Yeah, so a year ago at Unreal Fest, we presented version 1 of these tools, more like kind of version 0.5, like very baseline version. At that point, we were using ShockGrid exclusively as our database. And then we had our basic asset loaders and publishers. We had a render manager to send stuff out to the farm. And we showed an asset review tool. And since then, we've expanded that functionality a lot. One of the big pieces is abstracting our database. So we're using that as our sole source of truth rather than ShockGrid. And one of the big things that that means is it introduces interoperability. So you no longer have to use ShockGrid if you're working with our tools. You can use FTrack if you prefer that. And that also allows us to track more complex scene elements as well, which is really advantageous when working with complex scenes. We've also built a standalone task launcher, which can launch people directly into the program they want to use with the task. We have set and shot builders to load entire scenes and shots instead of individual assets. We have an asset linker, which we'll show in a little bit too, to link and create assets in the database as you're blocking out scenes, so you don't have to go back and do that manually. We've also introduced additional farm automations, allowing export and import of things to Unreal that happen on the farm rather than on an artist machine. You won't see that very visually in some of the examples we show, but that's something that goes on behind the scenes. We've also expanded our automated QC and introduced more integrations like OpenQ, Deadline, FTrack, like I mentioned before, and Jira, with more to come. And at the end of this presentation, too, we'll give kind of a quick peek at some of the upcoming tools that we're working on as well.
And so to give a bit a real-life example of one of our past projects, which we did this year, we were brought in by Epic Games to help teams of Pyramidination in Zebu to transition from Unity to Unreal for the LEGO Dream Show. The guys were transitioning mid-production to it, and they needed a quick way to rebuild the pipeline, and also they brought us in to analyze the process and see where we can find efficiencies. And I want to give one specific example on the lighting department. That before I mentioned that 30% it's an average, but then you have certain bottlenecks where like you can have even much higher efficiency gains if you look in and analyze. And so for we worked specifically with a lighting artist and saw that artists wasting a lot of time into importing the assets. They wasting a lot of time integrating the animation, integrating the sets, kind of replicating the lights from shot to shot, and also like pulling the assets from their storage to their workstations. So we worked with them to optimize these processes and pretty much automate all of it on the farm, like Chris was saying earlier. And so basically we built them a workflow that automates all of the task preparation for the lighting artist, and they can basically just open the task. We pull only the specific shots that they need to work in, not needing to try to update all of the 4 or 5 terabytes that your project is, and start working on the specific shots. And the way each individual artist was able to deliver 50% more shots on daily basis. And so today we'll be looking through what's from our side, like it looks like in practice. What do these tools do, and where do they fit in production? We'll be going through 4 stages of in our production, which we call blockout to gray boxing. We'll be showing like how do we approach the set building and kind of set dressing side, and then the final already like on the shot where we do previews and animation and to the final rendering.
Okay, so let's start with blockout and take a look at what this looks like in practice. So we'll start blocking out in Unreal Engine. That's one of the things that we strongly believe in doing and encourage other people to do as well, in order to take advantage of some of the real-time tools and start playing around with the creativity of the scene as early as possible. We try to use Unreal modeling tools to do our blockout. We also put in early versions of lighting and start doing scouting and setting up camera tracks within the scene. So our goal here is to block out the set in Unreal Engine with proper structure and naming of the levels and assets. We then need to link these assets to the database once they've been blocked out. So when the artists are creating the final version of those assets later, they know that this blockout should be a statue, for example, or this blockout should be a church. And then also track those assets through your database as well throughout the production process. Once that's complete, we need to publish the assets and commit them to source control. We use Perforce here, so all the examples are gonna be with Perforce. And then also you need to register that in your database. So that goes through our abstracted database and then is sent to ShotGrid as well, where you can read it and track task status and so on. And then update the task as well once the publish is complete. Also, we're in the middle of overhauling our UI and UX on this. But we want to show it to you as is. You guys know how it goes, I guess. Oops. OK, so first we're going to start by launching into the task using our task launcher. This is a standalone application. So the artist is able to select their task there, and then it'll automatically open Unreal. It'll set up your Perforce workspace behind the scenes and pull the assets that you need for this task. And then also, because this scene was not created yet, this level within Unreal, it'll automatically create the level structure with the levels and sublevels, since it doesn't exist, and give them the proper names as well. Then from there, we can actually start blocking out the scene using some simple Unreal modeled assets. And the goal here is just to get a good sense of the scene look and feel. You can see that we have some lighting in here already as we do this. And at this point, we also set up some early previs camera tracks as well. So this is number one, used to just get a sense of what the shot's going to look like. And then this camera track will also be used for scene review as well once it's published. And now we need to take all these blockout assets that we created, and we need to link them to the database. Like I said before, to know that this blockout right here is going to be a statue, and have the artist be able to know the context of the blockout models that they're going to be working with later when they turn it into final. And now we know which blockouts are associated with the final assets. Artists can also create new entities within the database as well if inspiration strikes them and they end up blocking out something that wasn't in the initial asset list. And from there, we're ready to publish our Unreal blockout set. So we do this with the publishing tool. We select our task there. It'll register all of the assets. We have automated quality control that confirms that the naming is correct, all the assets are linked, and any other things that you want to set up before your scene is published. And then at that point, when you hit submit, the level and assets are automatically submitted to Perforce, and that information goes to the database as well. And speaking of the database, so you can go in afterwards. You can view your review assets, which are automatically rendered within ShotGrid, and you can go and check out the scene. And here the horse on the statue is missing. So we'd want to say, fix that, please, and re-render it.
So this process, like Chris was saying at the beginning, it has a pretty big overhead in logistics, and primarily Artists, if without automation, they would have to start recreating the levels and then go manually rename all of the assets. Then somebody would have to go into the Excel spreadsheet or like error tables, like list them, and then another person would be importing them to ShotGrid, etc., etc. And so one of our main goals with this was automate the task beginning steps, so automate also the connection to Perforce and to all of the other storages as well, and have the artist just launching directly into the task. And through Asset Tagger, that was one of the biggest pains for us internally, that we would have additional people would have to go and then manually review them, or like enlist all of the tasks, all of the assets which were used there, etc., etc. And then we'll need to like relink them, and so it's a fairly manual process, which right now just goes all together. And same time, during our publish, we can automatically order the QC that all of the naming convention and project structures are done correctly. It can follow all across the rest of the production together. And for us, just on this specific task for logistics, we used to budget about 4 hours. Now we budget about 1 hour 75. So for us, total efficiency gain was 130%.
Okay, so let's move on to the next step here, where we want to turn our scene blockout into final assets and get started doing previs with these final assets as well within the scene. So our needs is we have to import this blockout into Maya from Unreal after the Unreal publish happened. We then need to model those final assets in Maya to replace the blockouts, using them as a reference. We need to texture the assets in Substance, and then we need to publish back to Unreal. So that's a pretty big round trip. And then once we're back in Unreal, we can start moving further with our previs, doing character posing, camera tracks, and so on, and eventually render that previs to the farm. So this graph is a very simplified way to represent both the workflow and the data flow. So the important thing to keep in mind is that the workflow, for example, for the modeling and texturing, moves from Maya to Substance, but the data in between is actually pushed to Perforce and then registered on ShotGrid, and then it's pulled by the next program that you move to. So here, once again, in Maya, we'll start with our task launcher. So this will open us in context of the task. And here, the artist has a choice. They can either use the set builder to pull in the entire set if they want context for an asset that they're working on, or if you have a whole set assigned to one artist, which oftentimes would be for smaller sets. With something big like this, you may break this out into specific tasks for individual artists. So individual artists would want to work on one specific asset rather than the full scene. So if you want to do that, then you can load just that individual asset in the same way using the asset loader. And then that'll bring in the blockout. So you can use this as a reference. You know the general size and shape that you want it to be within the scene. You see this early blockout of the horse. And then you can turn that into a final asset. And then once again, use the publisher to submit either that one individual asset, doing QC to make sure that everything looks good. Or if you were working on a whole scene, you can use the same process to submit the whole scene as well. And then that will save all those files to Perforce and let you know in ShotGrid that your task is complete and you're ready to move on to the next step. So for surfacing, we can launch straight into the task in Substance, again, through the launcher. Loading times sped up, of course, as this loads in. And now we're ready to create our final textures. So the launcher creates a really quick process to just get into it as quickly as possible. And once final textures are ready and they're applied, we can publish from Substance. We QC the material naming, and then they're exported automatically and uploaded to Perforce. And one of the things that we do is we track our materials and textures, and we register them in the proper slots. So when we move them back into Unreal later on, we can make sure that as they're imported, everything is already going to be set up properly, so you can begin look dev immediately. Now that we're back in Unreal, we use our set builder to load in our final set assets. Once again, the process is sped up for brevity here. So our assets are loaded in with our proper material assignment and coordinates. We make sure that everything goes to the exact right place within the scene that it needs to be. And we automatically replace our blockout assets as well. So the way we do that with our level structures is we have a separate sublevel for blockout, a separate sublevel for final assets. And then we just hide our blockout sublevel at the end. And then we'll do a look dev QC process within Unreal as well after that import happens. And from here, we move on to do our previs. This can kind of begin earlier as the final assets are still being created. And we like to do previs in Unreal as much as possible using the Unreal animation, rather than creating additional steps and trying to round trip that back out and in from Maya. And then once that's done, we can render that and send the scenes to review.
So here again, because this process, it's generally like very gruesome and kind of like takes a lot of iteration, and also just with sheer number of assets which were like used in this scene. Like we had to build about 45 various large assets like building churches, etc., and hundreds of like smaller elements. The logistics initially estimated were about 160 hours, and when we tested with tools, we came to about 89 hours for this. And you can see that basically the Maya and Substrate like shot builder and set builders and asset builders can give flexibility to the artist to just focus on specific tasks, import and set up, create the presets inside of the scenes, and then with the publish automatically update the status, propagate the files across your storage. And one of the like biggest updates for us was the Unreal Set Builder allowed us to entirely remove all of the kind of like horrible way of importing one asset one by one, renaming them, placing them in correct sublevels, and then go into each asset, place the textures, and kind of like start just go directly into the material.
Yeah, the other good thing about the set builder too is you can run it at any time to detect if there's a new version of any of the assets within the scene, and it'll pull in just those new asset versions as well.
And as Chris was saying, we often started the animation layout in Unreal because for us it's currently the animation tools in Unreal are already in a pretty good state that you can like quickly rough it out, or we also use various mock-up solutions like we have Xsense, and we also using Move AI, some others, so our animators can very quickly in Unreal lay out the shots, lay out draft animation, and then just click export, and we automatically export all of the FBXs and everything else for down the stream that people can start, as animators can pick it up in Maya and start cleaning it up and do the final animation sequences.
Okay, so let's move on to the final set of steps here and finish the shot. So for these last steps, we need to bring the latest version of the shot and level to Maya. And at that point, we can complete our final animations and then publish back to Unreal. And that includes both character and camera tracks as well. We're going to skip that step here just to avoid another Maya export-import video and try to make time. But you can imagine how that works. And then Unreal will pull those changes, pull our camera shots and character animations, and do any final touch-ups to the shot, lighting and effects and anything else. And then at that point, we'll publish our final shot assembly, and we'll send it to the render farm. So this is after the Maya portion is complete. We'll build our shot within Unreal, and this will pull in our animations and camera tracks at this point. So you can see we have our updated camera track with the final set assets that you saw from the beginning. And also, if we can, we like to make any final animation tweaks or small changes in Unreal with Control Rig as we're putting the final assembly together, so we do not have to go back to Maya. And this saves a lot of time if the hand is a little bit off or the foot's doing something weird, and you can go in and just make those changes in Unreal with the keyframes, as opposed to having to kick it all the way back out, assign it to another artist, and then bring it back into Unreal. And as Unreal animation tools have become more powerful, it's easier and easier to do this. And as these final tweaks are being made with the rest of the scene as well, at the same time, we work on finalizing our shot lighting and effects and making everything look pretty in Unreal before we do our render. So now we use our shot publisher to send the shot out to render. We'll use deadline here. And we select our shot, send it out, select remote publish, and then that'll send it out. The artist won't actually see this deadline screen that pops up here. It'll all happen behind the scenes. But this can be monitored by supervisors as well, just to make sure that the render is completed correctly. And you can automate notifications to send that out if it fails and so on. And we have our final sequence that can then be reviewed in ShotGrid after it's rendered. So you can check it out, give feedback, and send it back if needed.
And so again here, through automation for each of the iterations, we save about half of the time. And like Chris was saying, one of the biggest tasks, as always, it's becoming to import and update all of the cameras, characters, assets automatically, make sure that the latest versions are in there. And in this case, for example, characters were built in MetaHuman and then resculpted. We used for the groom, we used Maya. But clothing was done in Marvelous Designer, and then the simulation was done back in Maya. And then it was all re-imported back. And in the crowd, we have about a dozen of characters, so we would have to do every time for it individually, and every time then when the animation update or something else, we need to resimulate again and go through the full cycle again. The same for all of the assets. We used to run in a lot of problems with that. We have, let's say, one of the boxes or one of the crates had updated textures, and we see only after the shot was rendered and everything, we went through the full flow, that we missed this texture or an asset there. And so this way we're able to automate this process and fairly easily avoid the errors as well. Another part which we do in this, and Chris didn't mention that whenever we rebuild the shots on the artist workstations, we only pull the assets which they need for the specific task. On the final scenes, generally they're becoming extremely heavy, and you need to import. If you need to import a lot of close simulation and a lot of new assets, across multiple shots, it's becoming hundreds of gigabytes. So we're trying to limit as much as possible. And whenever we send it to the render farm, depending on what the task step is. For example, if it's just review or final, our render farm publisher automatically preselects the MRQ presets and publishes them to editorial and to the shot grid for review.
And here's a look at our final render with a lot of time saved along the way through pipeline tools. This is a little piece of a test short that we're making called Lightfall. We're not a dedicated animation studio, but we do a fair amount of animated content. And we're using this as a great way to test our tools and make sure our workflows are ironed out. And we also received a mega grant for this as well to work on tooling. So we're finishing it up. It should be released sometime in the not too distant future. You guys can check it out if you're interested.
And you can see for this just it's a small short which we're doing, but we had to build about 11 different environments and so you can imagine the number of assets and number of back and forth that we had to do to build that.
And our team is relatively small too, so efficiency is extra important for us.
And so, as we talked, Chris was saying at the beginning, we'll be showing also like some of our upcoming tools or what we're working on. And one of the big parts, like Chris was saying, like we're about 120 people, so in a lot of projects we collaborate with other studios, and we either hire as vendors or we share work with multiple studios across board, and also our clients oftentimes have to deliver to us either like project files or like assets from previous projects that we need to reuse for our own. And as well from ICVFX, for example, we create VAD, we create environments which need to be published then on the stage. And what we found through past years that this pass-off of files between the source control, like which we use Perforce, for example, or even other storages, create a lot of issues. And it's been very painful on many projects where last moment we like need to like dump something onto a box folder or just like get in the car and drive with a hard drive to pass it off to somebody. I personally sat for a couple hours in Burbank places, and the biggest problem of that you have security concerns between sharing accesses to your Perforce servers, because majority of time following it's either behind the VPN or internal the internal network, and or you have just limited amount of licenses, or you have proprietary tools there. The second problem that you might have your own project structure or like depot structure, stream structure, which is automatically mapped to your workstation. So the cross-compatibility of that can be problematic. And the third one, but also which is a big one, it's to merging the streams together or merging the assets together after they were updated from by one vendor or by the stage to bring it back. For example, a normal in-camera VFX workflow, it's for example, VAD house creates environments, ship it to the LED stage. LED stage does the recording, also does on-day edits and changes to the environment, and then need to send back the environment to the VAD house to kind of finish, do the final renders, etc., or share it with the VFX house down the line. And in the animation world and game world, we also see a lot of, for example, like majority of games today or like animation are shared between multiple studios, or at least using vendors to build environments, do lighting or specific tasks. And so to solve this problem, we contacted our friends at Perforce, and we kind of brainstormed with them on what can we do to make this easy, because it's across board, and we're talking with a lot of friends in the audience here that we kind of like would try to solve this problem. And so we came out with this multi-studio Perforce solution. It's basically the like management tools through a web UI, which automates connections between multiple Perforce servers together and gives you ability to select only specific assets which would be distributed across various vendors or various partners, and give you also ability to your partners or vendor to push back and submit back any changes. But before the changes are merged into your own depot, we run automatic quality control on it, and kind of if wanted, it goes into a waiting to merge separate stream, where it's like so it doesn't go directly into your main project and doesn't break a bunch of stuff in it. So today we'll show UI which we're currently working on for that, and we'll be releasing the product soon.
Real quick as well, just to preface. So we have built functional back-end core functionality for this, and we're still working on the front end for this product as well. So to be clear, what you're going to see here is UI mockups that show the flow, and then we hope to have this ready to go within the next few months.
And also, if you have any feedback, suggestions, or any pains to share on this and how it can be improved, feel free to share, and we would love to hear your feedback.
Yeah. So the idea here is that when you start, the owner who controls the master server that runs this will select a vendor and then add them to this, set up supervisors, and then they can choose which project they want to use and what stream within that project they want to share. So if you're pushing an initial project to somebody who's going to be a vendor, you can set that up ahead of time to make sure the level and file structure is set up in the way that you want it. So once they receive it, it's already good to go. And you can also make sure if you have any proprietary tools or anything like that, you can strip it out of that stream before you share it with the vendor. And then they'll only have access to that one stream that you want to share. And here's going the other way as well. When a merge request comes in from the vendor, they've succeeded at doing their scope of work, and then they send it back in, and now it awaits merge. So we'll do automatic QC. You can go in and check it out, and also look at individual assets, set up a review flow too, so you can leave comments on some of these assets if something doesn't quite look right. And then if everything looks good, you can proceed with the merge, and it will go back into the designated stream within your depot. And then also before this, this merge happens as well, it'll also load into an awaiting merge stream. So if you want to get a little more granular with your review, instead of just looking at the web interface QC, you can check it out hands-on as well before you make the decision to merge it in. And the web interface for this, think something kind of similar to Swarm, where it can list the commits and change lists, and you can go through as precisely as you want and see what exactly this merge request is going to contain.
And so our next initiative internally, which we've been building this year, it's internal code name, it's Olympus. The official name might change based on our friend here, Sinan, because we are really bad with names. But one of the main goals of this is to create a high-level studio management solution for ourselves, and we also will be licensed out to share with others. Because the reality is that the pipelines and workflows getting just more and more complex, and infrastructure is getting more complex. Through past years, we started moving into hybrid solution. We have our infrastructure split between dedicated server, location on-prem servers, cloud. We started in like our project management, production management integrations. I expanded. Right now in-house, we have projects which run using ShotGrid. We have clients who use FTrack. We have production who using Aeon, like OpenPipes tools. And also we use Jira, like Chris said, and UTrack for the game development projects. And so all of this data need to flow between each other. Another part is like I was saying, on the storage, you have Perforce, you have the Cumulo, and like in general NAS storages. And also your farm array expands, and where like you have on-prem farm machines in cloud. And the pipelines expanding. Like we showed, we have our own proprietary tools, but also, for example, Ion OpenPipe. They have a great array of tools for Houdini and for like editorial. So your editors might be using not in-house tools. Your clients or vendors or partners can be using ShotGrid Toolkit, etc. And so for this, we are building the Olympus to be able to merge this data all together and to be able to orchestrate the workflows. When we want to start a project, we want to orchestrate that all of the correct integrations are set up for this project. That on each artist workstation and on all of the storages, we create the right folder structures and we distribute the accesses. We're building out the integration with the resource management to have the user and access management as well. On one other side, it's also production analytics and financial. Because for us, like, again, I'm saying, for example, in-house, we use in U-Track, and we have, for artist management, we use either ShotGrid or F-Track. We need to consolidate all of this data to first make our CPAs and our CFOs happy, but then also to see where like the problems are and how we can optimize it. And the last point is that through across-board, across all of the projects, we generate a lot of assets. And we generate assets in different permutations and different states using different DCCs and also different versions of DCCs. Majority of time, it's a binary files, which, like, let's say U asset, you don't know, like U level, you don't know what's under it. And the asset reusability becomes very problematic. And being able to port from one project which was archived to the next project, the assets, as well been a problem before for us. That's why initially we started building our own abstracted database, how Chris was saying at the beginning. And that will allow to have more high-level IP management and more high-level asset management across our studio, to be able to not rebuild the same chair 75 times, but be able to extract it from one archive and easily reuse it into another without having a data loss or trying to figure out which version of Maya or Substance we used for that. And the last part, it's a workflow manager as well, which we built there to take care of all of the automations like QC, like file transfer, et cetera, et cetera. And this we plan to start beta testing closer to mid next year, and we'll see.
Yeah, so it's a long feature list, obviously. It's a ways off, but this is something that we've really been building towards this whole time with all our tools. So we're really excited to really dive into this and start fleshing it out even more. And also looking even more forward to the future. One of the things that we want to do is use this workflow engine combined with this master database in order to create a golden data set that can eventually, hopefully, be used with AI in order to be able to make artists and producers' lives easier. And this is all theoretical. There's a long way to go. But I think it's easy to see some low-hanging fruit examples of why something like this can be powerful. Being able to do faster previs and more creative iteration. Use your asset library from all your previous projects combined with prompts in order to create fast previs animation. Being able to translate storyboards into keyframe sequences using existing animation, existing assets. Also being able to do smarter and faster QC. Nobody likes to do QC. Nobody likes getting something kicked back to them if there's an issue. So for example, being able to use AI to analyze a UV map and see if there are any holes in it and propose a better variant or a fix to the artist who can do that with one click. Also from the producer side, which is a huge one. And that's something that having this data set combined with the workflow engine and everything else really enables, which is being able to predict bottlenecks before they happen. Being able to monitor all your system events, detect anomalies, and know ahead of time if something is going to happen that's going to affect your future delivery dates by being able to analyze your past productivity in order to predict what's going to happen in the future and really get ahead of things so you avoid having a last-minute fire that you're trying to put out when the deadline is looming on the horizon.
So I want to thank you to come listen to us and kind of learn about the pipeline with us. So we still have some time for questions if you want to come to the mic, or also we have our emails here, like, so feel free to reach out or see us after the session for a drink.
Yeah, thank you, everyone.
show. 3, get ready. 4, 3, 2, let's go. Go, go, go. On your mark, get ready, say go. Go, go, go. On that jump that, get up and go. Go, go, go. On your mark, you ready, yeah, go.
Okay. Give it a couple of minutes. Thank you. I worked very hard on that. It's very heavy, though, and completely impractical in this weather. It's a lot better when we do Game Developers Conference and it's like a balmy 65 degrees outside. Yeah. Yeah, I'm just gonna stand here. Hi, everybody. I'm gonna get this started a little early because this one takes me a really long time to get through. Hope you don't mind. Everybody trickling in, don't worry, this is just preamble. Thank you all so much for coming out. I really appreciate seeing all your lovely faces, and it means a lot to me that you're here. If you've not met me before, my name is Matt Oztalay. I am a senior developer relations technical artist here at Epic Games, and if you've spent more than about 5 minutes with me, you know that I care an awful lot about performance. So it's a good thing that we've got 45 today to talk about optimizing UE5, rethinking performance paradigms for high-quality visuals, part 1. As an industry, we've had a good 25, 30 years to figure out tips and tricks and tools to get the most visually sophisticated experiences we can out of our graphics cards. We're hitting 60 frames per second, 4K experiences that are really incredible. And then Unreal Engine 5 comes along and releases 4 brand new graphics technologies that nobody's ever used before that come with their own performance paradigms and ideas, and we're all expected to use them because they're pushing the boundaries of visual fidelity. And we also have to scale all this content from a high-end PC all the way down to an Android phone. And some of these performance paradigms are completely contradictory to how we used to build games or how we think about building our content. So that's kind of what I'm here to do today. I want to give you a head start and put a few tools in your tool belt so that you can get up and running with all of the incredible new graphics features in UE5. So today we're going to be talking about Nanite and Lumen, and then tomorrow at 11:45 in this very same room, we're going to be talking about virtual shadow maps, world partition, temporal super resolution, and scaling your content across a lot of platforms. I cannot cover all of Unreal Engine's next-gen graphics features in 45 minutes. Trust me, I tried. It's a lot to cover, especially if I want to get everybody up to speed. So I would love if you joined me tomorrow for part 2. And this is going to be an intermediate level talk. I'm assuming that you've got some general knowledge of scene optimizations and rendering pipelines. This won't be so much a discussion of how to go about optimizing scenes, since every project is going to have its own challenges and its own needs. Instead, I want to arm you with knowledge of how these systems work as it pertains to performance so that you can better understand the issues that you might be facing and how you can rectify them. Throughout this talk, you're probably going to hear me say, but that's a whole separate talk, and I will have a whole bunch of resources in the links at the end of the show, including some excellent talks from my colleagues about those systems, as well as a bunch of videos that I've made about general scene optimizations. And since we're talking about performance, this is normally where I would get up on my soapbox and talk about how budgets are a statement of your values, how performance is everyone's responsibility, and how you should be testing early, often, and on device. But that's a whole separate talk. In case you're unable to join tomorrow, I want to make sure to hit you with two really important things up front. The first is that with UE5, you have choices. You don't have to use any of these systems. They are all console variables. They are all project settings that you can change. You don't need to use any of them. Obviously, we want you to be using everything. I think one of the major things here is that kind of, you're going to see this throughout this talk, all of these systems are kind of interrelated, and they all work together in order to give you the visual fidelity, give you the kind of performance that we want out of these features. And you're going to see that as we go, and that's why, again, stay for part 2. And the other thing that I really want to talk about with performance is the importance of scalability settings. So when you boot up the engine for the first time, it's going to be in Epic Scalability. And you're going to find that up here in the settings menu and down to the engine scalability, right? This is Epic Scalability. Epic Scalability is where you want to tune for high-end PC, next-gen console, 30 frames per second. And then, if you're going for 60 frames per second, make sure you knock that down to high. We've spent a lot of time building out all of these different scalability settings so that they get you closer, they get you in the ballpark. I'm not going to say it's a magic bullet. It's going to get you in the ballpark for what you need to do for performance. What I really don't want you to do is to attempt to tune a 60 frames per second target at epic scalability. That's going to be an uphill battle, and you may end up having to make sacrifices that you wouldn't normally have had to make if we were using the right scalability settings. So that's really important. And I'm going to preface this talk by saying that we're talking about these features as they exist today. This is 5.3.1 from the launcher, which we released just last week. But know that the performance capabilities and stabilities of these features continues to improve with every release. And like I mentioned, this talk might run a little long. We may not have a whole lot of time for question and answer. We're going to go to the Dev Hub afterwards. Just out, turn right at the top of the escalators. Can't miss it. I will probably be living there if I'm not in this room. So don't forget about that. With that, let's talk about Nanite. Because polygons are free now, right? Not quite. The basic idea with Nanite, if you're unfamiliar, is it is virtualized micropolygon geometry, which is a lot. The basic idea here is, like, what if you could hand do every LOD for every mesh to perfectly match every situation? Doesn't matter if it's right in front of you, doesn't matter if it's 1,000 miles away, you have the perfect LOD every single time. That's what Nanite's trying to do. The basic idea is that we want to make sure that we're never drawing more triangles than we need. And in fact, we're going to try and keep that the difference between the detail that you can see and what we're rendering on screen within like a pixel, just like near pixel perfect LODs. This is what we're trying to do here. And so the big thing is we don't want triangles smaller than a pixel because those are very expensive for reasons that are going to be in a whole separate talk. But right, we've got our triangles, and then as we move away from those triangles, slow down, we're swapping in new triangles. We're simplifying the geometry so that we're only rendering the detail that we need to see. There is some free advice that I will give you at the top of the talk about Nanite. It is not just for high-res meshes. Yes, it's very good at rendering high-res meshes very efficiently, and it is also good at rendering low-resolution meshes very efficiently. It's a faster rendering path. It has a smaller data footprint than a traditional static mesh. And the one thing that I do want to say, too, is if you are using virtual shadow maps, because again, everything works better together, but with Nanite specifically, or with virtual shadow maps specifically, Nanite will make things go a lot faster, and we're going to talk about that tomorrow. And of course, our eventual goal is Nanite everything. This is what we're trying to get to. You saw we added landscape support in 5.2, programmable rasterization in 5.1. We've got experimental spline mesh support in 5.3. And of course, we mentioned displacement and tessellation is coming. So like I said, these systems are supposed to make your lives easier, and many of the best practices that we've developed over the years still apply when you're building worlds with Nanite. So there are still some ideas from pre-UE5 graphics and optimization that are totally valid. And a lot of those are going to come into play. All that being said, nothing is free, and I want to take a look at Nanite kind of from the top of the scene called down, because that's how I optimize my content. So if we do a little profile GPU, there we go. We do a profile GPU, we go into scene. The first thing we run into is this Nanite viz buffer. This is basically where Nanite figures out what it can see and what it needs to rasterize, and then it's going to rasterize it, which is going to lead into a conversation about Nanite overdraw. And then we're going to talk about how Nanite kind of messes with our idea of draw calls. And finally, we'll talk about mesh and scene construction. So with Nanite, we're going to do a lot of that. We're going to do that occlusion on the GPU. First thing we're going to do, hierarchical Z-buffer occlusion, fairly standard. It's going to catch a lot of the big stuff that we can't see. And then we're going to call primitives, similar to standard frustum calling. And then we get into instance calling. And the instance calling of Nanite is very similar to the way we do instance calling with hierarchical instance static meshes, which is a great thing. And then we get to the last step of occlusion, which is cluster occlusion. This is one of the really cool things about Nanite. So when Nanite ingests its geometry, it divvies your base mesh up into clusters of about 128 triangles. And these clusters are sort of like automatically generated LODs of clumps of triangles, as opposed to automatically generating your entire LOD. And when the mesh gets far enough away from the camera, when any of those clusters can be swapped out for lower resolution clusters, we're going to do so. And because we're doing this on a cluster by cluster basis, there's also, we don't have to have a single LOD for the entire mesh. If you've got something that's really, really long, you get the high detail stuff close to the camera and the low detail stuff that's further away, automatically. And then as an additional benefit, we get to call individual parts of the mesh. We can call these clusters. We don't have to call everything all in one go. So what this looks like, take a look at those clusters real quick. Right, so here are our clusters. And then you can see as we move away from those clusters, everything's going to get a little bigger. Whoop, flew into a building. And you can see at a distance, we've got bigger clusters for bigger stuff, but then when we get closer to it, those are going to get more higher resolution, right? Cool stuff. All right, so the next step, come on, there we go. So the next step is rasterization. We know what we need to rasterize, now we're going to rasterize it. And if you're unfamiliar, rasterization is really just what materials are covered by what pixel, so that we can then further evaluate it. And it's going to drop these into what are called bins. These are pre-allocated bins, and we can see what those bins are if we do a stat. We do a Nanite stats. And that's going to bring us this window, or this debug display over on the side, and you can see these raster bins and shading bins. We'll get to those in a second. And indeed, you can see that rasterization on the stats off in the profile GPU. So we can go into our scene, and we go down to Nanite viz buffer, draw geometry. Again, because this is how I optimize, right? We go and we see hardware rasterize and software rasterize. So what the heck are those? Turn off that Nanite stats real quick. Nanite stats off. There we go. So hardware rasterize, software rasterize, those are new terms. We've not seen that stuff before, which is kind of an interesting thing. There's basically two paths that Nanite can choose to rasterize, hardware, software. And software rasterization is kind of the true and proper Nanite. This is kind of one of the other really special sauces about Nanite. And it's when the triangles are getting really, really small. And I know it says software, but it's really compute. And it's really, really fast at rasterizing a lot of really small triangles. And then we've got hardware rasterization, which is everything that's kind of bigger triangles, or more traditional rasterization. This is the same stuff that we've always done. This isn't something that you really need to worry about, but I bring it up because if you're going to be trying to debug and optimize your scenes, you're going to go through the profile GPU and you're going to go, Matt, what's hardware rasterized, what's software rasterized? That's what this is. And if you want to take a look, just as a quick little thing, we can do r.nanite.visualize.advanced1, come on, 1, and that's going to give us a few extra view modes in Nanite. So we can look at the raster mode, and you can see all the stuff in blue. Those are really, really small triangles, and everything in red is hardware rasterization. Like I said, this probably isn't a thing that you're going to need to worry about in doing a lot of your optimization, but it is a thing that I want to bring up. So when we get into rasterization, the first thing that we're going to do is fixed function rasterization. This is for all of our opaque, non-deforming geometry. Basically, anytime the vertex is where it should be when the vertex is in the same place as it is in the static mesh asset. It's really, really fast, and it can rasterize the entire scene all in one go. But there are situations where the vertices or the material coverage of a pixel isn't what it is in the static mesh asset, and this is where programmable rasterization comes into play. There are kind of 4 or 5 different ways this happens, so world position offset, masked materials, pixel depth offset, and displacement. The top 2 being world position offset and masked materials, which we'll talk about. So then if we want to preview this, if we want to take a look at this, if we're debugging it, with our advanced Nanite visualizations, we can go down to raster bins. And everything that you see here in a color is using programmable rasterization. Everything here in black is using fixed function rasterization, which is very, very fast. And if you want to see how much time it takes to rasterize anything in your scene, we're going to do a r.nanite.showMeshDrawEvents1. And I know for the people in the back, this is going to be really hard to see. Don't worry, this is going to be on YouTube later. We can do showMeshDrawEvents1, and then we do another profile GPU. And we can come down into Nanite VisBuffer, draw geometry, main pass, and now you can see we've got little carets next to hardware and software rasterizer, and you can see all of so there's our fixed function, right? Super, super fast. And then we can see all of the different materials that require programmable rasterization. And you're going to see kind of stuff duplicated between hardware and software. We'll talk about that in a second. So the kind of big thing that's going to cause any kind of programmable rasterization is world position offset, right? I have a vertex, and I want that vertex over here sometimes. The thing that you really want to do when you're setting up your project is go into your default engine INI, which is not opening right now, but I will have more stuff on this in the links. You're going to go into your default engine INI, under render settings, you're going to add r.optimized WPO equals 1. And that's going to let us do kind of 3 things. The first is it lets us see when stuff is evaluating world position offset. So most of the stuff in the scene is not moving, it's not evaluating world position offset. That's totally fine. The next thing that it gives us, oh, sorry about that. The next thing that it gives us is is the evaluate world position offset checkbox that's going to be in the details panel, and it's also going to give us this world position offset disable distance. So there is a little bit of a cost to determine whether or not something is evaluating world position offset. General recommendation, if you don't need it, turn it off. And then the next thing we get, again, is that disable distance, and that lets us stop evaluating world position offset beyond a certain distance, does what it says on the tin, tautologies are tautological. And what that gets us is it moves stuff from programmable rasterization into fixed function rasterization, which again is very, very fast. So let's talk about this water wheel, because this is a thing. We got ahead of ourselves there. This is a thing that I have gone on the record as suggesting as a good idea. We have, what's the word I'm looking for? We want to optimize CPU time, so we're going to move some of these simple animations over to the GPU. We use world position offset. I did a talk about this in 2022 at GDC. That will be in the links at the end of the show. With Nanite, things get a little more interesting because instead of having the whole mesh and culling the whole mesh, we're culling the clusters. And if the geometry of the cluster moves really far away from where it was originally, things get really weird with Nanite really quickly. And so what you need to do is go into your material and set the displacement, the max world position offset displacement distance over here. And this is just going to tell Nanite, hey, this thing can move a little further away from where it was originally. If you don't do this, you're going to end up with like weird culling artifacts or smearing, or it's going to clamp the WPO, which is no bueno. But you do have to be conscientious of this, because this is the same kind of thing as if we went into the details panel and we oh, I didn't save that one. And we increased the bound scale, right? Because when we increase the bound scale for frustum culling, if something's off screen, we might still be paying to render it. We might still be rasterizing it. We might still be running its vertex shaders. That's all going to get very expensive. So it's a thing to keep in mind. There's also some stuff that's going to come up. Like, we're going to see this water wheel again tomorrow because there are some other considerations that come into play with virtual shadow maps. So that'll be a fun one. The other big thing for rasterization, programmable rasterization, is masked materials. Now, unlike world position offset, which we can disable and then switch to fixed function rasterization, masked materials are always going to be programmably rasterized. And this is also going to lead to an increased amount of nanite overdraw. So that's a lot of what you can see in that profile GPU was masked materials from a lot of stuff in the scene. And the fun thing about this, or the interesting thing about this, is that the masked materials are going to lead to nanite overdraw, or nanite overdraw is just a general concept. And this is basically the number of times that the rasterizer has to touch a pixel. And as we all know from being very good at general optimizations, we know that overdraw is bad. Anytime the GPU has to do stuff in series, one after another, is not great. We want to do more work in parallel. And this really comes down to the fact that Nanite is unable to rasterize the same pixel twice. So anytime stuff is overlapping, so you can see like there's a lot of overlapping stuff here, a lot of the foliage is overlapping, that's going to increase the number of times the rasterizer has to touch that pixel. And the flashing here, the jittering, that's because of the temporal jitter for temporal super resolution. We'll talk about that tomorrow. And some amount of overdraw is totally okay, but we want to really avoid closely stacked surfaces or surfaces that are kind of smashed into each other. The thing about masked overdraw is that, if we're doing nanite overdraw for this plane, right, we can go to that overdraw view mode, and that kind of does about what we expect. It's going to mask out a lot of the stuff behind it, and then we're going to have a little bit kind of around the edges for the clusters of some of those other primitives. Now, the thing with masked overdraw, in 5.1 and 5.2, the nanite overdraw view mode would look like this because we've already masked out those pixels, which is deceptive because if we go into it in 5.3, we actually updated it, and now you can see how the masked areas are technically being overdrawn. We have to rasterize the places where the masked material isn't going to render a material. That's just how we have to know about it. So if you are in 5.1 or 5.2 and you see maybe a more reasonable nanite overdraw view mode, keep in mind this thing about masked materials. And then if you upgrade to 5.3, you're going to get a more accurate visualization. And one of the reasons that programmable rasterization is so expensive is because in order to properly interpolate vertex attributes for the pixel shader, we have to run that vertex shader 3 times per pixel so that we know what are called barycentric coordinates, basically where that pixel is within the triangle, so that we can do that interpolation. That's why it's so expensive. So when you've got a lot of vertex shader, that can get really expensive with programmable rasterization really quickly. Whew. So you might have picked up on this. I've sort of danced around it already. Nanite differs from traditional rendering when we're talking about draw calls. Traditionally, same geometry, same material, that's one draw call. So there was a lot of stuff that we would do in order to reduce the number of same geometry and the number of same materials. But Nanite's a little different. Because geometry is changing every frame, because we're swapping out clusters, we're simplifying things, what same geometry means is kind of, we've got to throw it out the window. So really, for Nanite, it's just same material. And what's going to happen is the CPU is going to pre-allocate bins for those materials because it knows where all those materials are in the scene. We know that's an easy list for the CPU to pick up, and then it's going to pre-allocate those bins on the GPU so that Nanite can go, oh, I've got this material, I need to rasterize it, here's my bin for that rasterization, and then when it rasterizes it, it hands it off to the shading bin, and that's where, okay, I'm gonna shade these pixels. We'll talk about that in a second. So in this situation, I've got 3 shapes: sphere, cube, and cone. And on the top, those are non-nanite, and on the bottom, those are nanite. And they're all using the same material. So in traditional rendering, it would be draw, call, sphere, cube, cone. With nanite, however, because they're all using the same material, we can go to this material ID view mode. They're all using the same material. They're all in the same shading bin. We're just evaluating one shading bin. It doesn't matter what the geometry is. We've already figured that out. So in this situation, also I talked about this in the GDC 2022 talk, there are some other things that we can do to reduce the number of materials. That's what we're trying to reduce. Custom primitive data, per instance custom data, material parameter collections, those are all still perfectly valid things to do to reduce the number of shading bins. Now, one of the sort of interesting things that comes out of this, because the GPU is, or the CPU is doing that pre-allocation, and then we're culling a bunch of the clusters before we rasterize them, and then when we rasterize them, we're going to hand it off to the shading bins, and all of this stuff is pre-allocated. So if there's part of a material that is not on screen, we end up what I refer to is empty draws, because we might cull clusters that are completely off screen, but we still have that shading bin there, so, or that shading or that raster bin there. So if I go to my nanite stats again, you can see over on the side over here, come on, you're going to see raster bins, and we've got the number of empty bins, same thing with the number of shading bins. We're working on this. There's a thing that the engineers wanted me to let you know. We're trying to reduce the issues with empty bins. It is a thing for y'all to consider as well, and we'll talk about that a little bit more tomorrow. But our general goal here is going to be to reduce the number of bins, and we can talk about that here. So one of the first things that comes up with Nanite is, hey, if we've got all these bins, do we need to worry about instancing, right? Because it's just going into the same shading bin, everything's going to be totally fine. Well, using instant static meshes, all of that stuff is still really useful to use, especially for CPU overhead. The number of actors, as the number of actors increases, that's going to be more overhead for the CPU versus having one instant static mesh with everything built in. Hierarchical instant static meshes are kind of only necessary if you're targeting lower end hardware or platforms where Nanite is not available, because the hierarchical culling that HISMs do is sort of reduplicated by Nanite's instance culling. Now, you might have gotten ahead of me and realized that I was talking about instancing and same materials and world position offset and masked materials. I think he's talking about foliage. That's a whole separate talk that my colleague Nils gave at Unreal Fest Australia, and when that talk goes live on YouTube, I'll be sure to have that in the links as well. But the sort of short version of that talk is that there are trade-offs between the number of verts that you need to evaluate for world position offset and the amount of masked area of your material. So how much nanite overdraw do you want? How much vertex shader cost can you handle? There's a big map of this, and we haven't quite totally filled in all of the areas. But your options are basically, you can do traditional card masking, you can do what I call close masking. So you'll see an example of this in the Electric Dreams demo, where they kind of cut around the foliage. So a few more vertices, but not quite as many as going fully opaque and totally cutting out every little bit of the foliage. But those are options that are available to you. And then the next thing, that kind of leads into a discussion of mesh construction, right? Because again, polygons are free, but the question I get a lot is, how many polygons should I have? Because we're so used to thinking about that for GPU optimization, but Nanite's going to do all the work to simplify things. So do we need to worry about it? And I think yes, because it's going to have a bigger effect on your disk size, the package size of your project, and how long it takes to sync everything down. Because, right, sorry, I'm backed up on this. So just because Nanite is simplifying everything doesn't mean we don't have to be conscientious about the number of triangles that we're using. Yes, it matters for programmable rasterization, right? I think of this a lot of like an 8K texture, right? An 8K texture on a 4K monitor has to fill more of the monitor than we actually have in order to get to MIP 0. So in a lot of situations, are you going to see all of the triangles that you get when you're super up close to it, or is it going to be kind of further away and maybe you don't need quite as many triangles? So for example, the Quixel Megascans, a lot of that library for Nanite is about 2 million triangles. I've heard people suggest that 500,000 is a perfectly reasonable number. But the other big effect, like I said, is how long it takes to sync down all your content and how big it's going to end up in your install sizes. And what I'll say about Nanite is that there are, with these two considerations, the disk size of an asset, the size that affects your developers, that's the full U asset. And the reason that this can get quite big is that the U asset contains all of the stuff that we need to regenerate the cooked asset. You can even right-click on an asset and export the static mesh directly, and that'll be perfectly reasonable because all of that stuff is stored in that U asset file. So the disk size is going to affect your developers, and then the cooked size is actually going to be a lot smaller, triangle for triangle, than a traditional lotted workflow. That's just a function of the Nanite data structure. What I will say for larger productions who are using Perforce, we've got virtual assets, which is a whole separate talk. But basically, it strips the bulk data out of your static meshes and a few of your other asset types so that you don't have to sync down the full 5 million triangle FBX for a programmer who is never going to touch the static mesh. And then, of course, standard optimization tricks, make sure that your source and intermediate files are out of the workspaces that they don't need to be in. If people aren't re-importing stuff, they don't necessarily need to sync it. OK, so action items. What are we going to do with Nanite? We're going to profile. We're going to make sure that we're going to try and understand the problems that we're facing. Is it Nanite base pass? Is it Nanite viz buffer? What kind of issue is it within Nanite viz buffer? If we're going to make changes, we're going to profile those changes because we want to know that the things that we did actually improve performance. We're going to use instancing to make sure that everything is just sort of batched together in one draw call. That's just good practice anyways. And for Nanite, we're going to keep as much of our scene fixed function rasterization as possible by leveraging WPO disable distances and using opaque materials. And for Nanite overdraw, we're going to reduce the amount of overlapping geo and try to avoid a bunch of geometry closely stacked together. And of course, we want to minimize the number of empty bins. We'll talk about that a little bit more tomorrow. And we're going to reduce the number of shading bins using the same tricks that we've always used to reduce the number of draw calls, right? Cool. OK. Just take a nice little breather. Because next we get to talk about Lumen, Let There Be Light. It is our dynamic global illumination and reflection system, which gives us diffuse interreflection with infinite bounces and indirect specular reflections at scale. And before I talk about Lumen in depth, I also wanted to talk about standard real-time ray tracing, because I want us to understand how that works in context of Lumen. So with standard real-time ray tracing, for a given pixel, we're going to send out a bunch of rays from that pixel, and we're going to bounce them around the world to figure out what that pixel should look like, right? And the important thing here is that we're also going to evaluate the material when we hit stuff. The big takeaway is lots of rays from the same pixel, right? That's the most important thing to keep in mind about ray tracing. Lumen, on the other hand, has a bunch of tricks to reduce the number of rays so that we're now doing pixels per ray instead of rays per pixel. And the way it does this is it's going to generate a bunch of probes at pixels on the screen, and it's going to fire off rays from those probes. So that probe is going to cover a few pixels, and it's going to fire these rays off in the right direction. So we're going to do some important sampling from the last frame to figure out, hey, where do we need more detail from in order to get good results? And then when we're firing off these rays, if we hit something on the screen, we'll just use that information. It's already there. And then if we don't hit something on screen, so if our screen trace turns into a world trace, we're going to look up the results in the surface cache. So instead of having to reevaluate everything every frame, we're going to cache off the material and direct lighting information of the world in its own little cache. And we're going to asynchronously update. We're not going to update the whole thing every frame. That's expensive. And so we're going to use our probe results for global illumination and rough reflections. And then for reflections, we're going to send out rays from those pixels because we do need a little bit more information for reflections, of course. So what are you going to say? You're going to ask me what the surface cache is. Like I said, we're pre-computing all of our hit results so we don't have to worry about it later. It's this big 4K texture, and all of the stuff in the scene is drawn into this. And we can actually see this. We can visualize this. If we come up into our scene, we go to Lumen scene. This is what Lumen sees. So when I say, hey, we're going to go hit something, or if we don't hit something on screen, this is where we're looking up our results. And if you ever need to debug anything in here, we want to look at the surface cache view. So the yellow stuff in the surface cache view is stuff that is not being rendered into the surface cache. And anything in pink is where only part of the stuff is being rendered into the surface cache, just based on distance or size, because Lumen is going to pick the stuff that it thinks is the most important. And then with Lumen, we've got, of course, some stuff to consider. The big question with Lumen is going to be hardware ray tracing versus software ray tracing. And then we've got Lumen scene lighting, Lumen screen probe gather, Lumen reflections. All of this stuff is going to show up in your stat GPU, your profile GPUs. And I get to talk very briefly about async compute. So if you're looking at Lumen timings on consoles, things might be a little strange because it's being run sort of in parallel to the GPU work. Just a thing to keep in mind if you're like, why is Lumen costing 0 milliseconds? But then we also want to talk about the responsiveness of Lumen and, again, how we're going to build our scenes for Lumen. Right at the top, the big decision that we want to make first is if we're doing hardware ray tracing or we're doing software ray tracing. I know I just talked about hardware rasterization and software rasterization with Nanite. I need you to purge that from your minds. We're talking about something different. I know it's hardware and software. This is likely a decision, especially if you're doing this on consoles, where we want to make this decision up front. Which one are we going to use? And it's going to depend on the kind of experience and the kind of project that you're developing. So for software ray tracing, that's where we want really fast results. It's really good when you've got a lot of kit bash stuff that's overlapping instances. I'll explain that in a second. And then hardware ray tracing is for higher quality. You've got a lot of skinned meshes that might be significantly affecting GI and reflections. And if you have a lot of mirror-like reflections that you're worried about. So for 30 frames per second titles, we figure a budget of about 8 milliseconds for lighting and reflections is fairly reasonable. And that's perfectly achievable with hardware ray tracing on console. And then for 60 frames per second, we figure about 4 milliseconds is reasonable. And software ray tracing is able to hit that. And as you heard earlier, we're working on getting hardware ray tracing down to that as well. So with hardware ray tracing, what are we doing, right? This is hardware, it's ray tracing. It's what we were just talking about. It uses the actual silicon on the chip to do its triangle ray intersection math. These are your RTX cards, the dedicated hardware. We're going to trace against BVHs, bounding volume hierarchies. Nanite, hardware ray tracing uses the Nanite fallback meshes for that tracing. We'll talk about those tomorrow. And in order to do this very efficiently, we're going to rebuild what's called the TLAS, the top-level acceleration structure. And the cost of doing this is proportional to the number of instances in your scene, which we want to keep below about 100,000. So if we go to stat scene rendering, right? Stat scene rendering. There we go. We get this ray tracing active instances. This is the number we want to watch out for with our TLAS rebuilds. And we can move stuff out with stat. Come on, where'd we go? There we go. And we can move stuff out if we do visible and ray tracing is going to be the checkbox that we're going to check for that. You want to pull kind of smaller stuff out of it. We're going to do like ray tracing.culling.radius to kind of bring in the number of things that we have to worry about. And the other big thing to watch out for with hardware ray tracing is instance overlaps. So we can go to ray tracing debug, go to instance overlap, and this is going to show us where, hey, when we're sending a ray through the world, how many times do we have to calculate whether or not we hit something? That's a big thing to keep in mind. And I've got links at the end of the show for both the Lumen performance guide and the ray tracing performance guide, which go into a lot of detail with this. But the cool thing is with hardware ray tracing is that we can get more detail, more information. It's going to be maybe higher quality. Whereas with software ray tracing, which So hardware ray tracing is heavily affected by the instance count and the instance overlaps in your scene. Software ray tracing uses distance fields for its traces instead of actual triangles, which makes it go a little bit faster. Again, it's software. We can't really trace against a lot of ray triangle intersections. And if you don't know what a distance field is, that's just like a simplified mathematical representation of our geometry. It's going to be lower accuracy, but again, it's very fast. And then we're, of course, using our scalability mode. So at high scalability, we're going to use the global distance field, which is lower accuracy still, but again, very, very fast. And if we want to reduce our costs here, we're going to just set affect distance field lighting. We can just turn that off. But the cool thing about software ray tracing is, again, the cost of software ray traced Lumen is independent of our instance counts. But of course, with Lumen, because we are asynchronously updating that, if we, for example, very quickly change our time of day, Lumen is going to take a little bit of time to update, to catch up to our time of day changes as our sun moves across the sky. Now, what I generally recommend with this is instead of using a lot of the console variables for Lumen, instead we want to focus on the post-process volume. So if I want to increase the speed that Lumen is updating at, I'm going to do that in the post-process volume. Because a lot of the settings for Lumen in the post-process volume are sort of aggregates of console variables, and in a lot of situations you might have two console variables that that work toward the same goal, but maybe this number needs to be the reciprocal of this number, and if you only change number A, then something weird's going to happen. So again, post-process volume. And then if we fire that off, if we increase that speed, it means that Lumen is going to update more of the stuff in the surface cache every frame, which gives us more responsive lighting results at a higher cost because we're rendering more stuff at the same time. The other big thing with Lumen is our reflections, right? So Lumen is modulating its reflections based on roughness, which is really, really cool. And there's a cutoff. That cutoff you can see down there on the screen is when Lumen is going to decide to either use the GI results or if it's going to send out dedicated reflection rays. More rays, more cost. And the default number for this is 0.04. So we can see our kind of like dirty mirror here that is increasing roughness as we go. And then if we just change that r.lumen.reflections.max roughness to trace, if we bring that down, maybe that's going to send out fewer reflection rays. That's going to lower our Lumen reflection cost. And maybe we don't necessarily need to be sending out a lot of dedicated rays at a higher roughness. There is a separate toggle for this for foliage, so the two-sided foliage and the subsurface shading models. In a lot of cases, you might be able to just set that to 0, and everything will be totally fine. And while I'm on the topic here, I want to talk about some debugging with Lumen, because I do have some time for that. So if you go down to Lumen, go to Screen Traces. So like if you're not sure what Lumen's doing, we can just remove stuff from consideration. So in this situation, we've got this church over here, the town hall rather. Learn to read. And parts of the town hall, again, it's on screen, so we can just use those pixel values. That's super easy. But for the stuff that's not on screen, we're using the global traces. We're using the Lumen scene results for this. So if I'm like, hey, is that a screen trace that I'm seeing, or is it a world trace? I can just come down to the Show menu, Lumen, and then disable screen traces. And you can see, like, maybe the town hall detail isn't fully realized in the Lumen scene, but it gives you a place to look, a place to debug things. Now, one of the big things with Lumen and mesh construction that I think can sound very contradictory is that Lumen does very well with kit bashing. Because when we kit bash stuff together, we have these smaller modular pieces that we can make lower resolution distance field representations of. Because if I have, for example, a big old house, like this one, and it's all one static mesh, this is a thing that we used to do. We have tools in the engine to do this because we reduce the number of same geometry. But now that we have distance fields, the distance field representation of this would need to be really, really high resolution because of all the empty space in that house, which can be very expensive, both in terms of memory and evaluation cost. So instead, we want to build things modularly. And the great thing about Nanite, again, everything works better together is that if all of our modular pieces are all using the same material, then we don't have to worry about individual draw calls for all the different parts of our modular kit because, again, it's all the same material. And then the other big thing with kind of big, chunky structures and Lumen is that in order to draw all of that stuff into the surface cache, Lumen, when we make a new static mesh, is going to place a bunch of what are called surface cards. And I'm going to show you that visualization here. It's going to be a little busy. Visualize.card placement. And you can see all of the surface cards that we're using to project that mesh into the surface cache. That's how we're going to be drawing it. Now, the other big thing with Lumen is that we're rendering this stuff into the surface cache really, really small, right? Because 4K texture might not be able to handle everything on screen, so we're going to make it a lot smaller. And do you know what's really good at rendering stuff at really low resolutions? Nanite, huh? So again, everything works better together. What I will say about, and sort of because of that, when you're building out your scenes, when you've got hierarchical instance static meshes, foliage, for instance, and you want to make sure that they're contributing to the Lumen scene, they do need to be Nanite because drawing the numbers of non-Nanite hierarchical instance static meshes can be very, very bottlenecky for Lumen. So that's a thing to watch out for. I talked about mod kits, distance fields. That's great, that's great. We'll talk about Nanite fallback meshes in part 2. Doing good on time. Okay, so talking about Lumen, action items. What are we taking away from this? Hardware ray tracing. We're going to pick it if we want higher quality. We're going to watch out for our instance counts at our instance overlaps. Software ray tracing, we're going to use effects distance field lighting to remove stuff, and we can kind of tweak our roughness to trace value to control our reflection costs. Okay, so in summary, test early, often, and on-device. Make sure you're testing with the correct scalability. If it can be Nanite and you're using Nanite, it should be Nanite. And we're going to remember to pick hardware ray traced or software ray trace. That's a big decision we're going to make up front. And finally, I promised links, so you can scan that QR code. It'll take you to a link tree that has a lot of extra resources, the recommended reading for the end of this talk. And if you would like to ask any questions, you can come up to that microphone. And if you want to talk some more specific stuff, meet me down in the Dev Hub. I'm going to be walking down there basically as soon as I walk out of this room. So thank you all so much for your time and attention. Thanks for coming out. And I will see you tomorrow at 11:45 in the same room.
for the money. 2 for the show. 3, get ready. 4, 3, 2, let's go, 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 go. On your mark, get ready, set, go, 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 go. On that jump, that get up and go, 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 go. On your mark, you ready, yeah, go. show. 3, get ready. 4, 3, 2, let's go. Go, go, go. On your mark, get ready, set, go. Go, go, go. On that jump that, get up and go. Go, go, go. On your mark, you ready, yeah, go. show. 3, get ready. 4, 3, 2, let's go. Go, go, go. On your mark, get ready, set, go. Go, go, go. On that jump that, get up and go. Go, go, go. On your mark, you ready, yeah, go. the show. 3, get ready. 4, 3, 2, let's go. Go, go, go. On your mark, get ready, set, go. Go, go, go. On that jump that, get up and go. Go, go, go. On your mark, you ready, yeah, go. yeah, go. show. 3, get ready. 4, 3, 2, let's go. Go, go, go. On your mark, get ready, set, go. Go, go, go. On that jump that, get up and go. Go, go, go. On your mark, you ready, go. Show. 3, get ready. 4, 3, 2, let's go. Go, go, go. On your mark, get ready, set, go. Go, go, go. On that jump that, get up and go. Go, go, go. On your mark, you ready, go.
Good. Okay. All right. Hello, everyone. Thank you for joining Unreal Fest 2023. Very excited to have you here and join my session. Thank you so much. And today, what we're going to be doing is looking at look development using Substrate and Lumen. Now, before I dive in a little into the technical parts, I'm going to do a quick overview of what's going to be talked about in today's session. And I'll start with a quick presentation of myself. So my name is David Baylis, and I work as a tech marketing consultant at Epic Game / content creator. I also run my own company called David Baylis Design, in which, as you can see, I create lots of cars, all in real-time rendering. So all of these pictures that you see here are done using Unreal Engine 5, using Lumen, and the Substrate workflow, all captured in real time. Now, my role at Epic is to create, as I said, content creators, so create some content, and it's really about conveying the image to the user. So every time there's a demo content or highlights to do, such as Unreal updates, I would be creating some images to showcase that. So the first image that you see here, which is the cyberpunk city, that was the highlight on the Unreal Engine 5.1 release. We just wanted to convey the image of Lumen and global illumination, and Nanite also. The picture below here, you must be familiar, that's the Electric Dreams demo featured with the R1T. As it was featuring a car, I was asked to be part of the team and do a bit of look development. I actually did not do the exterior part, I did the interior, which at the GDC demo was probably shown for like 2 seconds. But I got my 2 seconds of glory there and I was happy. And by the way, you can play the demo at the booth in the lobby downstairs. And then the 2 last images, these are on the 5.3 release. This was to convey the image of the latest VDB import feature. So again, playing a bit on the Halloween theme and getting a tornado. And the last image, architecture visualization, just showcasing the new orthographic view. Anyway, with that said, today we're here to talk about substrates and Lumen and how we can achieve photorealistic looks using these 2 features. So this is the scene that I built using those 2 features. And we're going to see a bit about lighting and how to use Lumen, Nanite, and a bit of Substrate to really push realism into your scene. Now, let's start a little bit with lighting and Lumen fundamentals. The first thing I do in my scene is always use the color calibrator. I always do that because I just want to make sure that my lighting is correct and not too underexposed or overexposed. So I always bring in the color calibrator not only to check my exposure, but I can also check the reflections. Let me jump into the scene here in real time and see what I'm talking about. So here in the editor, I'm using the calibrator, and this is a mesh that you can get, by the way, in the engine. So if you want to do that, what you want to do is go into the settings here, And just make sure that show engine and show plugin content is enabled. And then in the content browser, you're going to go to engine. And I'm simply going to type in color calibrator. And I have my mesh that is right here, and I can just drag and drop this. So this is what I did with this one. Very, very useful tool for you to calibrate your lighting. Now, as I said, I can check my white levels, I can check my black levels. Pretty easy with that. I can also just double check that the reflections are working pretty good here. It's capturing the sky, it's capturing the environment pretty good. And for that, I just want to make sure that in my post-process volume, if I go down into the reflections right here, actually let me put the widgets a little bigger for you so you guys can see. So if I go into the reflections here, I am using Lumen. In Lumen reflections, I do want to make sure that I'm using hid lighting for reflections. If I switch back to project defaults, we can see that it's not capturing the essential of the environment, right? So I'm just going to make sure that is set to hid lighting for reflections. It does take a bit more of the performance, but we're here to make it photorealistic, so we're going to bump everything up. Now, new in 5.3 also is the max reflection bounce here. You can control the maximum reflections on reflection. So it's really, really useful to do that for automotive or reflective surfaces. Now you can have correct bounces on reflections. So that's pretty cool. Now, one little tool that I use, and that's quite a little bit hidden, is that I tend to measure the gray value on the gray sphere right there in the shadow area. And I'm going to measure that by using the pixel inspector. Now, if you go into tools and go to debug, and you want to use the pixel inspector right here. Okay, so I'm going to launch that. This is going to bring me a utility widget. And if I start going into the magnifying glass here, now when I hover my mouse over the gray value, you can see that very last value here changing. So right now it's reading 0.25. And that's usually a great value. So the normal value you would want to be in is 0.18, and that's sort of a neutral value. Here I'm overexposing just slightly my scene, but I'm not in that crazy range of 0.3, 0.4. That would be way too much. So here, just hovering that and just seeing that value is reading pretty nicely. So very useful tool for me to inspect my lighting, making sure that everything is lit up correctly. All right, so second thing that I use a lot is lighting channels. I use that a lot because I don't want my character to be too blended in the environment. I like to highlight the actor a little bit more. Specifically with Lumen, you've got to give it a bit more light. With path tracing, it's okay, but with Lumen, you might need to give it a bit more kick in the lights and bring in a bit more lighting to your actor. So I'm using lighting channels right here for the actor, and I'm going to demonstrate that in the scene here. So I've got my main actor here, the rider, and I've got my two lights. If it shows, there we go. So I've got my two lights here, red and purple. If I go to my details panel and type in channel, I'm using light channel number 2 right here, as you can see. So for my main actor, I'm also using light channel 2. So if I deactivate that, it's only receiving the light from the environment, right? But I'm telling it, hey, I want you to get hit by these two lights right here. Now, if I bump down this light a little down here and go to a white value, I'm just going to show you why it's important. Not only just to highlight the actor, but if I start moving this around here, I'm getting a bit more reflections, if I manage to get it. I'm getting some nice reflections on the visor right here. So it's also useful to get a little bit of highlight on reflective surfaces. I also like how it gets a bit of specular highlight just under here on the neck area, giving it a bit of sweat too. So that really just carries a bit more mood into the image, right? So super, super useful elements that I always use just to highlight my actors. Another important feature here is using Nanite. So Nanite and Lumen work extremely well together. So not only it improves your performance, it also improves your lighting considerably. Now, I've made some tests to believe that and to see the difference between the two. So it does a big improvement on global illumination and specifically ray-traced shadows. So here's an example with Nanite off on the foliage. You might think, oh, that looks okay, right? We're getting some nice foliage and everything, but that is with Nanite off. Now, when I turn it on, we're getting a bit more shadowing area, specifically in the back. So I'm just gonna go backwards and forward so you can see the difference between the two. And that is really just using Nanite on the foliage. So it's really just grabbing a bit more shadows there and everything. So very, very cool feature to use. It improves your performance and your lighting. Now, sometimes when you use Nanite, you might run into some issues like this. So you might have ran into this issue already, and that is because it's using ray-traced shadows. So the reason why that is because it's casting the shadows on the proxy mesh when using ray-traced shadows. But if this happens, don't panic. I know that is the first thing we do usually, but don't panic. We've got two solutions here for you. So either we choose solution number one is to simply get rid of ray-traced shadows. But what if you want to use ray-traced shadows? Well, solution number two is using a console command, and that is going to be r.raytracing.nanite mode 1. Let me show you. So I'm going to go into my second scene here. And this is using ray-traced shadows, right? So let it load. So I'm getting those errors that you can see, even though I'm using Nanite. That is because my directional light here is casting ray-traced shadows. So I'm just simply going to type in ray trace. And here you can see that cast ray trace shadows is enabled. Now, if I disable that, problem solved, but not exactly, because we're losing some detail in the background also. So I want to keep them on. And instead, I'm going to go in the console command and type in, I can simply type in Nanite mode. All right, and r.raytracing.nanite mode, and put that to 1, and that is going to solve your issue. So what it's doing is that it's using the fallback Nanite to 0. I like this command a lot because not only it works with ray trace shadows, it also works with path tracing. So if you were to go to the path trace mode, if it loads up, it will show the full Nanite mesh and not the proxy mesh anymore. So very, very useful command I'll put the slide back again until Path Tracer wakes up. So r.raytracing.nanite.mode 1. There we go. Path Tracer is awake. And yeah, so we're seeing that it's retaining all that information with the Nanite mesh, even with Path Tracer. This takes little to less to no performance. I've not noticed any performance hit using this command. But again, beware. If you're making a game, that could be different. All right, so I'll go a bit about the scene breakdown here, a little bit on the scene and how I achieved the render here with the mountain bike. And really the goal of this was to use all the features of Unreal Engine 5.3. So Substrate, Lumen, Nanite, and the movie render queue also. So this is not shot in Path Tracer. This is really just using Lumen. Everything is, shot raw inside Unreal using the movie render queue, disabling the anti-aliasing in the movie render queue, boosting up the samples, and voila, you get the results. Now, how I achieved this for the water splash specifically was to simulate water. So I needed some sort of simulation program, and what I am comfortable with is actually a plugin called PhoenixFD. It's developed by the V-Ray guys, and I use 3ds Max. And this really just allowed me to get that simulation working. So what I did is that I took the front frame of the bike, and I rotated the axis of the tire and the wheel on one axis, keyframed that, ran it through the simulation, and it worked. So the first few tries I had to nail down was the buoyancy and viscosity of the liquid, right? Because I was going through a mud puddle inside Unreal Engine, so I needed something not too dense, but not too light either. So you could control all of these parameters inside PhoenixFD. I believe you can do that, or you will be able to do that with EmberGen too, with their liquid simulator. So what I did is I exported all of that using Alembic cache, so a .abc file inside Unreal 5. And I could have exported that in simple FBX, right? But the ability to have Alembic cache was to run an animation if I were told to do so. So I was just preparing that in case I was like, oh, I might have to do an animation on this. Now, I always like to do my work, everything inside Unreal, and try to avoid post-processing as much as I can. So if I can take out Photoshop out of the process, I do so. And I try to create interesting techniques to get water splash in on the bike. So what I did is I just used a simple plain card with an alpha mask. Very, very cheap trick that's been used in games for years. Used the brush here in Photoshop, imported it inside Unreal, slapped that on a plane, and just moved it next to the wheels. So I could get a bit of particles and foam going there. Now, one interesting feature of this also is using the control rig. So that is a very, very cool feature inside Unreal 5 that allows you to have a custom rig for your character, and you can change all of that in real time. So the plan here was I could have gone with a pre-posed rider, right? But it was sort of hard to get the real pose, going through a puddle here. It was sort of hard to imagine that. So what I did is that I used the control rig feature inside Unreal Engine. So doing a quick demo here, if I load my sequencer, and I'm going to focus back on the rider right here. Now I have my final shot here, but sometimes, I'm not satisfied about, how the rider is or how does he look like. So I can just change that. If I go here in the control rig, I can change the pose of the rider dynamically and just get a feel of the change and the pose here. So this really allows me to dynamically see what's going on in real time and just get a feel of my scene here. So using the control rig inside here, very, very useful tool. All right, so let's move on to the substrate fundamentals here. And I kept that in the talk sort of for the last section, because I know it can be a bit overwhelming to switch to substrates. For those of you who are using legacy, I've been through there, and trust me, it's not that bad. Like it's actually pretty good, and you can really do some amazing results using substrates. There's a lot of helpers also that we're going to be looking at also to help you transition from legacy to substrates. Now, a few fundamentals of what is substrate. So substrate replaces material abstractions, subsurface, opaque, translucency, metalness with scientific parameters. So you can get really intricate with details on different surfaces. We got the opal material right there. That was used for the R1T in the Electric Dreams demo. That was using opal. So you're getting that multi-layer system. It is a more expressive and modular framework, provides a greater range of surface appearances. You can do much more accurate clear coats or dust on clear coats or liquid on metal type of work now. So enabling substrates is pretty straightforward. You want to go into the project settings, go to the renderings tab, and enable substrate materials. Now it says experimental, right? It's still an experimental feature. So if you do have a important project that you're working on, make sure to have a backup of this before going to the substrate way. Once you take that, you have to restart your project and wait for a bit, because it's going to be compiling shaders for a long time. So you'll have time to grab a coffee or something until it compiles all the shaders again. Now, what happens to my old legacy shaders, right? So all of the legacy shaders that I was using in the previous is going to be automatically converted using the substrate legacy conversion. Now, what I do, for example, is I start with the legacy. I do all of my look dev in the scene using the legacy workflow. And then when I want to get a bit more technical on materials, I would do the switch right then, right? And all of my materials would still be working. This would be the case for, let's say, automotive materials, right? If you're doing automotive materials or you're very comfortable with the way the legacy shaders are working, you can work on that and do all of your magic in there and then convert to substrate later on the process. Now, the main substrate layering nodes are these four. And there are four, but really there are three here that we're going to be using. And I try to make this as easy as possible for you to understand what we're going to be doing. We got the substrate coverage weight, which is essentially good for overlaying dirt on the surface, so very useful to do that for dust on clear coats, for example. That's going to be our substrate coverage weight. The next one, horizontal blends, I translated that to a sort of a linear interpolation. So if you guys are familiar with linear interpolation with legacy, that is going to be the node here that simulates that in a way. The third one is probably the most important one, and that's basically going to stack the multi-layers for you. So you're going to have layer 1, 2, 3, 4, and you'll be able to stack that with the substrate vertical layer. Now the last one, it's there, but it's recommended to stay away from it. That's what it says in the doc. It's there if you want to do a add node. You have it there, but it's best practice to stay away from it. Well, I've never used the add node in Substrate. I essentially use the vertical a lot. Now let's jump in back into real-time Unreal and do an example here of Substrate. All right, so let's exit my camera. Let's get the viewport getting big here. And what I want to do is I'm going to drop in a sphere here, right about there. Okay. And I've obviously enabled Substrate here. So I'm going to go into Materials, and I'm going to right-click and simply create a material as you would in the legacy. And I'm going to call this Chrome Dirt. And I'm going to double-click on this. And open the material here. So it says Substrate UE4 default shading. I can delete that. And now we have our main attribute here. Okay, so you can follow me along here. And we'll do this all together. I promise you it's going to be all good. So what I want to do here is I want to create a substrate slab. Okay, so I'm going to type in substrate, and we can see that slab is highlighted right here for us. Okay, and that's essentially going to be our layer 1. Okay, just remember that. That's going to be layer 1. Now, you can see that we have our diffuse, we have roughness, anisotropy, normal, so on and so on. But we do have two different nodes here, which are F0 and F90. And that basically is those scientific parameters that you can enter in for metalness, and F90 would be for the grazing angle reflectivity. So if you're coming from a legacy workflow, you might not know exactly what values to input here. Well, that's fine. We actually got these helper nodes for you. So I'm just going to type in here diffuse, and this is going to outline me a substrate helper. And I have one called here substrate metalness to diffuse color. So I'm going to use that, and here we have our legacy outputs, and then we can output these to the correct nodes. So I'm actually going to use this here, and I'm going to create a albedo and put this to white. Connect this to the base color. And metallic, that speaks to me. That is, I know exactly what to do with that one, so I can just drag and drop that one in here. Connect this to the diffuse, and F0, I can connect that to F0. I'm going to connect that to the front material. Hit apply. And what I'm going to do also is I'm just going to drag and drop this right here. And I'm going to bump up the metallic to 1. Okay, so now we're having a metallic surface. I just want to bring the roughness down to 0. So this is going to be my roughness chrome. And essentially what we're going to be building here is I'm going to be overlaying some dirt on the chrome material and show you why Substrate is different from the legacy, because we're going to have that top layer laying on top of the chrome. So I have my roughness chrome here, all good, and this is pretty much it for layer 1. I'm going to create a second layer, so I can just Control C and Control V on the substrate slab here. And I'm going to connect my F0 to the second one. Let's put this slightly reduced here. I do have a roughness map here that I'm just going to bring in right here. That's going to be my dirt layer. And here's the cool thing. So I want to control a bit the contrast and the low, the mids, or the highs of the dust here. So what I can do is I can just type in 3-point levels. All right, and that's going to allow me to control the levels of this map, which is basically black and white, and I can control these values much easier. So I'm going to create a low here, and this is going to be my mid, and this is going to be my high. So I'm just going to enter these correctly. All right, we have everything linked up here, so that's going to go to the roughness right here. And I'm just going to make some space here. We want some space, so I'm just going to disconnect this to the front material. Remember that first node that I showed in the slide that was really good for dirt overlaying? That was called the substrate coverage weight. So I'm going to be using that one. So I'm going to drag a node and call it, look for substrate coverage weight. All right, that's going to be my main node. And I'm going to name this dirt weight. All right, and then I want to link this main layer 1 to layer 2, so I'm going to be using that vertical node now to define the thickness between the two. So I'm going to link this to Mr. Vertical here. All right, and I'm going to connect my second layer to bottom here, and then I can just create a thickness node. Just a simple constant 1 is fine for now. Create that to the top thickness. Connect that to the front material, and we're almost good to go. Now, what I like doing is for the vertical node, if you want to control the thickness, you would want to use a node called the subsurface mean free path, because you want that surface, the light hitting that surface and going through actually that first layer, right? So we're just going to create a subsurface mean free path for the first one here. And again, just going to type in mean. I like this one, free path. And I'm going to connect the MFP here to the subsurface, and that's going to allow me to have control over the thickness of the material. Now I'm going to hit apply, save this. So Substrate does have a bit more, it does take a bit more on the performance side, right? So you just want to be aware of that if you're doing this. And then I can apply this to the material here. And let's go into the details. Yes, let's go into the details right here. So static mesh, element 0, chrome dirt. Okay, awesome. And I'm going to create a material instance on that one. That way I can access parameters much easier. So I'm going to enable all of these. and start playing around with some values until I get something pretty good. So let's go into the lows here and the roughness. There we go. We're starting to get something. So if I turn down the roughness to 0, okay, and now we can see a bit of dust on that metallic surface, right? So I can actually boost that, and I can play with the dirt weight here. And you can really just see the difference between using the legacy or substrate, right? Because if you were using legacy, you would use a roughness map, but that's not going to read through that chrome sphere, right? It's just going to be one layer. What we're having here is that we're having 2 layers, and that's that dust is actually reflecting pretty good, and it's doing its physical values here for the chrome sphere. So we're actually reading that clear coat on the material pretty well here. Now I can also play with the thickness of the material that's going to blend with the vertical layer that I told you, and you can really have a nice speckle of dust here. That's exactly what we use for the Electric Dreams demo, for Mud Splash and so on and so on. This was exactly the method used for that, which is pretty cool. So that's an example of using substrate with a simple chrome sphere material. Just to show you the basics of it, there's a lot of helpers in there for you to start using substrates. And once you dive into it, it's actually a lot of fun. You can do lots of cool things. You know, there's that opal material that you can dive into and look on how that was done, and it works amazing. Now, as I mentioned, working with layered materials here, that was the purpose of the talk here, to really just showcase the droplets and a bit of dirt on the frame of the bike, right? So what I've done here is, for the scene, it was really important for me to get not only dirt on the scene, but also some water droplets on the bike frame, right? I really wanted to capture that also. So let me jump back in the scene here quickly and just show you a little bit of the breakdown and get a zoom on the scene. So I'm just gonna go F11 here. And let's go down here on the materials and just see the different layers and everything that's going on the frame. So we're getting clear coats. That's one material parameter, and we're getting some dust, and we're also getting some water droplets right here, right? So I've also done this on the fabric, so it works on pretty much you know, any material that you want to do, right? So I'm going to go on the bike frame right here, and we're having some cool different water droplets here, obviously on the tires. So what I did here, let's jump back into minimized window, and let's go to the material output here, and let's see how this was structured. So a little bit more complicated, but not that much, to be honest. It's I'm using a first layer, which is the dirt, the rubber material, and I'm connecting that to the vertical layer. So just to get that you know, top and bottom thickness, I'm using a fake caustics here, which I'm using the horizontal blend this time, which is the linear interpolation node that we were talking about. And here, that would be my water droplet. So I'm just mixing the caustics here with the normal map that I downloaded here to get some water droplets in my scene. And all of that is driven here with the droplet mask, which is essentially driven in the coverage weight here. Now, this allows me to, if I get a material instance, so let's make just this a little bigger, and create material instance. I'm going to put this on the rubber right here, and let's enable a couple of settings here. Now you'll be able to see all the stacking of all the different, what the different materials are doing. So I can change the water caustics here on the droplets. I can change the intensity, and this is not changing my underlayer, right? So again, very, very cool to have control on this. What I can do is I can also affect the roughness under that droplet layer and start really just customizing everything in my engine to get a very cool feel about and realism in my scene. So all of the materials that I used here on the bike were using this, and this really just let me achieve higher realism, specifically in reflections, because that was a sort of a drawback. Before it was good, but the difference between Substrate and Legacy is really good. Yeah, so the goal of the scene here was really just to use Nanite, Lumen, and Substrate all together, making sure that I'm hitting that point to get everything looking good, realistically speaking, combining with Nanite and getting a good performance right here. All right, thank you so much for your attention. And if you have questions and answers, please ask me right now. You can also join me at the booth downstairs at the Twinmotion. I'll be there to answer all of your questions. Thank you very much.
show. 3, get ready. 4, 3, 2, let's go, 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 go. On your mark, get ready, set, go, 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 go. On that jump that, get up and go, 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 go. On your mark, you ready, yeah, go. show. 3, get ready. 4, 3, 2, let's go. Go, go, go. On your mark, get ready, set, go. Go, go, go. On that jump, that get up and go. Go, go, go. On your mark, you ready, yeah, go. Show. 3, get ready. 4, 3, 2, let's go. Go, go, go. On your mark, get ready, set, go. Go, go, go. On that jump, that get up and go. Go, go, go. On your mark, you ready, yeah, go. say go, 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 go. On that jump that, get up and go, 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 go. On your mark, you ready, yeah, go. show. 3, get ready. 4, 3, 2, let's go, 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 go. On your mark, get ready, set, go, 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 go. On that jump that, get up and go, 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 go. On your mark, you ready, yeah, go.
Hello, we're live. We're here. We're live.
Is my mic working? Yeah, there we go. All right, we'll just give it another minute, wait for everyone to kind of come in from the break, see how everything's going. Everyone having a good show so far?
Snoop Dogg's going to be here tomorrow. Woo!
Good times. All right, let's do this.
Right, hi, I'm Mark Lintott. I'm one of the directors for engineering at Epic Games. Some of you might have come to my talk on developer iteration last year, and hopefully you got some good stuff out of that. Hopefully we're not repeating ourselves again this year. We've got some new stuff to share with you and some feedback on some of the things that we've also implemented live and that are available to you now. So yeah, and Daniel.
And I'm Daniel Tutino-Galletti. I'm the technical product manager working closely with Mark and the core engine team. It's like the guts of the engine and really what helps basically everyone in their day-to-day lives. And we're here to talk to you about some of the things that we've been going through the last couple of years, how we've been evolving, but also how we want to make sure that you guys have what you need to be the most efficient and optimize workflows within UE. So one of our core guiding principles in everything we do is about faster iteration and efficiency leads to higher quality. This is something we truly believe in how we not just only build games, how we build the engine itself as well. And hopefully this translates to your everyday lives and how we see the efficiencies we gain from what we're doing can help you in your day-to-day. And the goal here is we want to save some time for Q&A at the end to make sure we get some of your questions. A lot of what we're presenting to you is stuff we've heard and listened from the community, but also what we live and breathe day to day, building the experiences we do. So this should come at no surprise. Some of the ongoing trends, as project data sets are only getting larger and larger. When we compare what we had yesterday to today and what we're forecasting in terms of growth and size for tomorrow, Whether it's for photorealistic content or stylized content, things are just getting bigger. It's a given. And of course, how we're trying to handle that is through scaling to the cloud, bursting to larger compute resources, leveraging storage. We have hybrid distributed teams at Epic and how we work. That's distributed in the sense that we have studios across the world, but also ever since the last few years, we've adapted to a bit more of a work from home hybrid work. Not everyone's in the studio. People are at their home offices still, really kind of benefiting from just the best efficiency we can give. And so a lot of the solutions we put together are tailored to that. Hopefully that resonates with you as well and what you're seeing in your studios. And this is the conversation we want to have with you. So in the core team, in the foundation team, as we call it, our mission is really about evolving those foundations of the engine's data pipelines, really making sure that it can handle that growth, that scale, and any ambitions you have that you're really trying to crunch the data through the engine. And how we're kind of tackling that is through 3 major pillars. Is about accelerating those syncs, from revision control, and how that basically speeds up your editor load times. The quicker you get into the editor, the faster you could iterate. But also, throughout the whole pipeline, how you build. How can we reduce those cook times? How can we make it faster and easier for you to package and test and iterate on your games? And of course, that's to do with the various consoles and target platforms you're going at. It's not just about, in the PC on your desktop, but also, hey, you're targeting 5, 6 platforms. We want to make sure that it's the most efficient, easy process possible for you guys. So just a quick recap of what we've done for Unreal Engine 5.3. Basically, where are we today in that mission? This is basically things that we hope will help you in your day-to-day and that you could try out right now. So part of that is virtual assets. This is something we've talked about for a few UEFests and a few sessions in our roadmap. So officially, virtual assets are production ready in 5.3. This is something we've been using at Epic for over a year and a half now, and then some. And just a quick recap, virtual assets are basically a separation of the structured data and the bulk data for an asset. So essentially sync what you need on demand. What I mean by structured data is you have the properties, settings, and metadata for an asset, such as a texture or an audio file. And then the bulk data would be the pixel data, essentially, the bulk of the time it would take to sync and transfer that. And so really what it does is faster, smaller project syncs, reduce that footprint on disk that you would have on your local machine, so you don't have to sync every single byte to your project if you're not using it or you don't need to edit it. And really what it also means is across, whether it's local or through a shared derived data cache or DDC, that means you can deduplicate that data across your projects, across users who are sharing that cache with you. And in Fortnite, we've seen up to a 4 times reduction on content syncing, just like the time it takes to bring in the latest revisions and synchronize that data so you can go and edit and basically play the game and continue your work. What that means for 5.3 is right now it supports textures, audio, static meshes, and Nanite meshes. So I highly recommend if you're working with large data sets and you're collaborating across multiple projects with those data sets to try it out. Kind of requires Perforce as a revision control, and that's something we'd obviously like to hear from you guys. What else would you like to see in terms of revision control support and anything moving forward that would make your lives easier for us to help you be more efficient. Next up is the Unreal Cloud DDC. Now, this was really our answer to accelerate sync times for distributed and remote teams. And what that means is, people who are essentially not in the studio, not within the firewall, but working from home. And so how could we bring that data closer to them? And so what we ended up doing was essentially taking that same logic of that shared studio DDC, but making it a cloud-native solution that has active and passive region replication. So for example, North America, East and West, Europe, Asia, wherever you need to replicate it, that's part of it, is inherently part of the system itself. And there's logic built into the system to auto-connect. So if you're somewhere closer, you'll automatically connect to that DDC rather than connect to one that's further away, which would defeat the purpose of actually synchronizing things faster. Enterprise-grade login with OIDC, essentially OAuth 2 as a foundation, so that could help actually protect your data. And the fundamentals of it right now is it's available as source. We call it experimental, but on a surface level, this has been production tested and running within Epic for over a year as well. What we're hoping to do next is basically productize it a little bit easier for you to deploy. And one of the ideas we had was to make a Docker image ready to go so you can deploy it on AWS. We have instructions available for Azure as well. Now, if those aren't your two cloud providers, again, we'd love to hear everything you're working on, essentially. Maybe it's Google, maybe it's private data centers. How could we help basically tailor these solutions to meet kind of your needs? Next up, we have a multi-process cook. And so this is really about essentially taking what has been a very single-threaded cook process and finally being able to leverage the extent of the hardware in your local machine. That could be a local machine under your desk, or that could be a single machine within the build farm. And what that basically means is you can now configure the cook process to allocate different cook workers from the cook director. So for example, we have it configured for 4 additional workers per node, whether it's a build farm node or it's a local machine on a developer's desk. And we've seen drastic improvements just from that alone. Now, of course, this is still something that's in beta. And what we caution is you try and test it out. Try and find the right mix of, depending on your system memory and how many cores you have, and of course the data you're cooking, try and find that best combination to give you the right performance gains that you'd expect from this. Basically, anything else to do with that? I'd say with, of course, one thing to keep in mind, is debugging. So being able to actually debug across these multiple threads now and configuring your IDE, such as Visual Studio, to be able to do that as a critical part of that workflow. And so everything you see here, you should see this on our public roadmap as well on unrealengine.com. Please check it out. If we don't get a chance to answer your questions on it here, go to the roadmap and actually tag your comments, put some votes on what you'd like to see. And with that, I'd actually like to hand it off to Mark to kind of give you a bit more of an in-depth detail on where we're going next and building on top of these foundations.
Cool, thanks, Daniel. So as Daniel says, I'm going to talk a little bit about beyond Unreal Engine 5.3, and this is all about how we build on the items that Daniel have just talked about and where we see ourselves going in the next year or so and where we want to get to. And really, this is all about us telling you what we think is the right direction to go in, and I'd love to hear from all of the people out there whether, certainly if they agree this is the right way to go, and if we've forgotten anything, I'd love to hear what that might be, and if there's any questions, then we're at Dev Hub tomorrow from 9 a.m. So if you don't get to ask questions about it today, please come and see us tomorrow at Dev Hub at 9 a.m. and we can talk about some more. So let's start with where we are today. So this is a kind of really simplified view of how editor data flow works today. And this is sort of prior 5.3. So typically, studios will have, when you boot up the editor, you'll have a local DDC. And all the work that goes into that is written as loose files. So there's loads and loads of files. Probably you also have a shared DDC as well. So something on your network or something, some people put them behind VPNs, which works and doesn't work. But typically there's some shared instance, and hopefully there's something that you have, instead of having like a local DDC for every project, hopefully your developers have a shared DDC on their workstations. Out of the box, Unreal creates a new DDC folder for every project and every workspace that you have. And if you're not using a shared DDC today, then please do. You're just copying loads and loads of files around on your disk. So that's the number one thing that I ask you. If you're not doing that today, change it. This all works really well, as Daniel says, for co-located teams, so people in the same studio and so on. But that's not really what modern day development's like. In Epic, we saw this as a problem when we went into pandemic, and a lot more teams now globally distributed, and Daniel will mention that in his part about Unreal Cloud DDC. So, we really hope that more and more of you get to leverage Cloud DDC, and we want to make sure this is something that's available to everyone. As I talk through the next number of slides, Unreal Cloud DDC is actually critical for some of the features that we're gonna build on going forwards. So that covers the general editor case, but there's more to the problem than that. We also have to cook and stage the data. And anyone who's done cooking and staging knows that as soon as you cook the build, it sets a whole bunch of new files in the saved folder. And then when you stage, you get a staged folder with a whole bunch of new files in. And then when you pack, you get another package folder with a bunch of new files in. So we're just creating loads and loads and loads of files. And the files don't really know about each other. There's no sharing, and especially even these things don't even go in the DDC, right? So even if you have a shared DDC, multiple projects, multiple CLs, multiple workspaces, all create loose files. This is just wasted disk space, time, and effort for developers wanting to iterate on target. And it gets even worse. So once you've created all these files, then you need to deploy them to a target. And this is often where we get the slowest part of the iteration process, like taking a full stage build of Fortnite and then copying it over to your PS5 to test it is a long and laborious process. It's another thing that blocks you from iterating fast on target. And depending on what target you use, that can be a fairly quick process. From Switch, it's a small data set, it goes over fairly quickly. With whole PS5 build, some of these games are like 150 gig these days, and copying that over just so that you can iterate is an absolute pain, right? And this is why most developers just choose to use Pi. I mean, there are a number of developers that can only work this way. If you're a console programmer looking at optimizing stuff on platform, you have little option but to do this. And really what we want to do at Epic is move to something more like what we call play on target, where iterating on target is something that not just is something that our kind of console engineers do, but it's something that's a reality for every developer. So every content creator is able to run their game on target. So how do we do this? So let's just first address that loose file problem, right? So we've got files everywhere. We've got files for, as I said, for stage builds, package builds, all sorts of stuff. So the first step is to centralize this, and this is what we call the Zen server. So Zen server is it's not a product name as yet. It's probably going to be called something different by the time it lands in licensees' hands. But Zen is more of a concept. It's a way of working. It's a way of structuring our data that runs from one end of the pipeline to the other. So the very first thing we can do is replace that local DDC and that shared DDC with the Zen server. As far as the editor and the cooker goes, it doesn't notice any difference, right? You can enable a Zen server. The editor will automatically spin it up for you, and it stays around as a service for the entirety of your working session. And it says completely hidden from the editor, and the only thing you would notice like switching over is maybe some increase in disk space, and that's simply because you've got all this trash living in the old DDC and all these other folders that you just need to delete. So instead of writing millions of files all over the place, we centralize it, and it's not just about removing the loose files, it's about modeling loose files in a different way. So pretty much all of the content, if you think about virtual assets from Daniel's slide, almost all of the content that we use from source assets right up until stage data is by and large structured data and bulk data. Bulk data is often duplicated between stages. You can end up with the same bulk data that you generated in the DDC ending up in the cooked game. We're not taking advantage of that. So all of the way it works is that all of our file types are modeled this way: structured data and then content addressable bulk data. And you can think about Zen as a bit like a virtualized file system. We can do tricks like partially load the bulk data. We can run the game without the bulk data being there at all. We can sync it on demand. If we know that we've got a bunch of bulk data that we're going to need soon, we can schedule it and asynchronously load it. So we're going to follow this whole path all the way through. So back to our target iteration problem. What if we didn't need to generate that stage cook data or that full package data to iterate on target? And yes, we've got things like cook on the fly that sort of did this in the past, but that process is mostly unreliable. What if we could just stream that data directly to the target? And with the Zen server, that's exactly what we can do. On every target platform, we will allow you to cook. Your entire game will be cooked to the Zen server. It will deduplicate any bulk data, and you will be able to stream it live over to the target. So this removes that staging process, and it also removes that deployment process. Now, I understand that that's not always going to be the case, right? So pulling anything across the network is going to be resulting in a lower bandwidth and a higher latency than maybe it would have been pulling off the SSD. But the point is for most developers, this probably isn't a critical thing, or at least I feel like our view is that that's not a critical thing for all developers. Yes, if you're working on a streaming game and you want to get performance and I/O is really critical to you, then you'll always want to deploy that to the machine. But yeah, at most cases, I think it's probably fair that people can iterate just using this. But as I said, yeah, cook on the fly, it sounds a bit like cook on the fly, right? And yeah, it pretty much is. This is going to be the kind of replacement for cook on the fly. We were going to make cook on the fly too, but this is essentially covering that whole thing. And the problem with cook on the fly, though, is it relies on iterative cooking, which today is mostly unreliable, and we're going to discuss that next. So, okay, the problem is, in order to get to that stage where we can deploy stuff really quickly to the target, we have to have a full cook of the game, right? And things like multi-process cook will help with that. We've seen, as Daniel says, we've seen 2.5 times cook improvements just by using multi-process cook. And when I started at Epic, cooking a local build a fortnight would often be 20 hours. Today, it's somewhere around an hour and a half or 2 hours just for the cook stage. There are other front-end prologue and epilogue pieces that add up with that. But as I said, iterative cook was this, is one other way where we could, hopefully just cook the game once and then iterate on top of it. But as I said, it's mostly unreliable. It kind of works, right? The reason why it doesn't work in every case is iterative cook relies on asset dependencies. And if we can reason about asset dependencies, then we can look at whether an asset's changed and know whether we need to recook it. Well, for most types, that works, but for some types, it doesn't. It doesn't work for all types, and that's often where this kind of unreliability of iterative cooks comes from. It's that kind of, you don't know all the asset dependencies, so you end up having to cook everything again anyway, just to be sure. So we're going to solve this problem in 2 steps. The first step is to be 100% reliable iterative cook, right? And the way we do that is there's some types in the engine that we can reason about that we know are good citizens of iterative cook. And the simple solution is to say, fine, we'll take all of those types away and we'll allow you to iterate on them. And hopefully, and we think, they're the similar kind of types that we've targeted for virtual assets, textures, shaders, meshes, that kind of thing. And that will always be 100% iterable. The rest, we local cook, and we hope that the improvements we've made with multi-process cook and other optimization of the cooker means that the rest of that data maybe isn't so much. So, maybe in the future we can look at a 30-minute local cook for the entire build, and then just iterate on the things that have changed. So that mostly works. And I said the reason it'll be 100%, but the missing piece of the puzzle there is that it's not just about asset dependencies that mean you have to recook something. One of the other parts of the problem is that the code changes and the schema for the objects change. So just because you cooked it, you can't be sure that once you get the latest code build, that it will still be usable. And so that's what we're calling incremental cook. So this is step 2. Incremental cook is going to use object schemas. It's going to, again, look at the types that are data safe as well. The schema will allow us to put things like, typically the sort of black holes we get into where we get unreliable are like custom serialization functions where, there's if PS5 do this, if PS3 do this, if Xbox do this. And those are the things we can't reason about for, changes in data and changes in code, sorry. Or adding new properties and such means that, a binary stream is no longer usable. So being able to model that as an external data structure means that, we will take things like, the if PS3, if PS5s out of that, model those as data, and then we can much more reliably reason about code changes as well. So another thing that impacts cooking time is loading, right? So we often, with cooks, we just often load the asset, transform some of the data, and then write it back out again. More often than not, we're loading data that we don't actually use when we're in cook. This all adds to that time. So going back to the Zen way of doing things, if all of our data is structured data and referenced blobs, then we can take advantage of this and know if we don't need that data for cook, we just load it, we only load it when we need to. So what we call lazy loading is something that we're going to be rolling into our Zen loader. So yeah, so if you don't touch the data, it'll never get loaded. And if it's at the point when you touch the data that it does. So there's a lot more optimizations just from how we load data when we cook. And this same Zen loader methodology also applies to just regular editor loading as well. So you might load a level that's got a massive audio sound bank in it, and it's only when you actually use that audio effect do you really need to load it. So it's stuff like that that will really help, I think, with just normal editor loading as well. So we've talked about how we might get faster local cooks. Great. But that's, again, we don't just cook locally, we also cook on the farm. Most of our time of generating these packages for testing happens on the build farm. And we've seen with the Fortnite case that, oh, hello, I'm still there? Yeah. I've seen with the Fortnite case that multi-process cook really gives us some good returns, but we can't ever hope to use incremental cooking on a build farm. We're not a typical build farm anyway. If you've got the same build agent that you use to build your game, and you don't wipe the data between the cook, you could incrementally cook with that, right? You've got the state that stays on the build agents. But in the modern world, and especially the way that we work at Epic, we typically lease a whole bunch of AWS nodes, and then we use them for a cook, and then we return to the pool, and the next time we get an agent, that state is lost, essentially. So incremental cook isn't necessarily applicable as it is today. So what we're introducing is a thing called a Zen snapshot. So this is, once you've finished your cook, we store the state. And remember, this is just the metadata. So we're only storing what the cook output was. We're not storing all the individual data blobs. They are already in the DDC. They're already shared. They're already in your shared DDC. And with a Zen snapshot, think of it, it's kind of like a Perforce shelf, right? You finish your cook, you shelve the changes, and then the next build agent pulls that shelf down, unshelves it, and then continues iterating from that snapshot. So using that, an Unreal Cloud DDC, we're able to then not only use it for the build agents and incremental cooking, we'll also be able to use it for distributing builds as well. So our builds are stored in the Zen server. The Zen server is replicated with Unreal Cloud DDC. So getting builds to your developers that are in the other side of the world should be a much easier process than it is today. So one last trick. How do we make local iteration faster, even faster? So if we can cook our data on the build farm, and we're able to store that Zen snapshot, and a build machine can pick it up where it left off, why can't we do that locally? And that's exactly what we're going to do with Zen snapshots. So you're a local developer, you come to work, you go off to the build farm, you find the latest build, you use a Zen snapshot, and that will essentially unshelve that build to your local machine. And from there on, you can iterate on top of it. So you don't, in the future, we're hoping that you won't have to do the first local cook. You'll be able to use the Zen state from the cook that happened on the build farm. And then, yeah, maybe there's some slightly different, you've got some slightly different code and data. And this is where incremental cooking, without incremental cooking, you couldn't do this. Your data, your assets might be slightly different to the build farm. But we should be able to reason about those, at least for a majority of those good citizens. And you would only just need to kind of locally cook an even smaller piece. And really one of the other cool things about this is because it's all using that same content addressable structured data model for Zen, you may already have most of the build on your machine already. If you synced last week to the build, you're only gonna pull the deltas. Now, even more cooler is you don't even have to pull the deltas. You only have to pull the snapshot. And once you start running on target, you essentially could run with just streaming that cooked data as you need it on demand. So you don't even have to like sync the whole of that data set. You only have to sync the things that you don't have locally. And so you can reuse parts of the build you already have. And this also means things like A/B testing or switching between builds and so on and so forth. It's all Delta. So you're doing those kind of operations, which I think is fairly common for most of us, should be much, much quicker in the future. OK, I'm going to hand over to Daniel.
Thank you, Mark. And so everything we've kind of covered is looking at how we work today and how we're trying to optimize as best as we can. A lot of it is a brute force approach to just multi-process cook, for example, throw more cores at the problem, can we iterate faster? And part of what we're exploring next is really how can we evolve not just how we build games, but also in how we ship the game itself. How can we make things a bit more modernized and not just this big monolithic chunk that we have to build every single time. As Mark was kind of saying, we're trying to iterate more quickly, build what you need, sync things on demand. And so everything we're going to kind of cover next is more thought experiments that we're kind of prototyping in-house. We'd love to hear your feedback on how you see yourselves go through these same challenges and understand, how can we make things smoother, better, stronger, faster? And so one of the things that we're kind of in the process of looking at and heavily inspired by how UEFN works today is what we're calling the cooked editor. And essentially what this means is we're trying to, we've seen the performance gains of loading data into UEFN. A lot of it's all cooked data, except for the stuff you yourself are bringing in to the editor. Whether those be raw, meshes, audio files, textures, whatever, is currently limited within the scope of a UEFN project. How can we expand that and make that, basically viable guidelines for yourselves, developers and content creators in your pipeline? Something that you could use when working with Unreal Engine binary builds to really get those same benefits. Separating that editor data from the runtime data. And so, leveraging everything you've seen, Mark cover with Zen. The next kind of phase would be, OK, how could we then potentially look at workflows that involve asset hot reloading? You're working off cooked data. You just need to make that one edit. How could we swap that back to a source data file, allow you to modify it, continue working, potentially even recook that in the background automatically? And with the right build CI processes, you should be able to technically achieve that. Now, of course, what we don't quite know yet is, depending on how the content creators want to iterate, should these things be more automated? Should it be more manual decisions that people have to essentially queue and then choose to receive the cooked data back? We're still exploring all of that. And so I'm going to let Mark kind of cover a bit more, also in the same vein, how we're trying to modularize how we build games.
Hello, back again.
That was a quick switch.
So yeah, games are just getting bigger, right? They're just getting huge. Typical modern games, 150 gig downloads. Games are just getting bigger. Obviously, the normal way of solving this problem is divide and conquer, right? And that's exactly what we're taking for what we call modular game builds. So, we're learning from the methods that we've employed for UEFN, right? Which is leveraging on game feature plugins. So the way that we want to develop our products for the future is to split. You can think of it every feature or every level, that you could split those off into a game feature plugin. And the idea is that when we talk about cooking on the build farm at the moment, if we look at Fortnite today, it's like cooking this feature and then this feature and this feature and this feature. It's all done in one long serial process. Even though each of those steps is multi-processed, what we want to be able to do is kind of go, well, there's this core bit of the game. Maybe it's like your game hub, something like the minimal like the lobby on Fortnite, for example. We call that minimal lobby. The idea is that you have a really small piece of your game that that cooks first, and then you cook all of your features in parallel. So you reduce, you're not reducing the overall compute time. You're actually reducing that critical path. And that has lots of benefits as well for things like if a particular level in your game has got a bug in it that doesn't cook. Today, if you cook everything as one monolithic build, that screws the build completely. Whereas if you can break those off, you can also have that bit of redundancy in there that says, hey, this level's broken, but all these levels are testable. And the fact that it's a game feature plugin, the way that we work with the game feature plugins is we design the system so that the product still runs if the game feature isn't there, right? So it means you can do this kind of partial build, and you can always guarantee to get something at the end of your nightly build, even if parts of your game are broken. But not even that. It's something that we also want to provide for our players as well. If you get Fortnite today on the Switch, it's like 20 gig. Switch Gen 1 has only got 23 gigs of usable disk space. And we know that going forward for the metaverse, we couldn't ever hope to ship it all on that, and be available on that Switch. So we're leveraging this same model of modeling our games and game feature plugins, and we're able to separate certain plugins off as on demand. And we upload those to a CDN, and we're able to kind of download those on demand when the players need it. So what it results in is a smaller upfront install. And yes, it means that the player has to maybe download something a bit later on, but it gives the player a choice about what they want to engage with. It makes it easier to get bigger products onto smaller hardware. It means quicker engagement. Someone hasn't got to find 150 gig space. I went to look at Forza Horizon the other day on Game Pass, and it said, I need 140 gig. And I was like, oh, no, I've got to go and delete something. So we want to get away from that model of people having to find space and have to download this big thing. I mean, games that are 20 levels long, and that player isn't ever going to reach that. It's a bit like the Play Go thing, right? The player isn't going to reach level 20 for another 20 hours, so why the hell are they downloading it up front? So it's one of those models where we want to apply this not just the shipping product, resulting in smaller packages, choice for players, but also for how we develop games, how we build games, because they're only going to get bigger. And then related to that, and again about getting things only when you need it, Daniel mentioned earlier on virtual assets, and that is just a source asset prospect. But what we're going to be, we're evolving the way that we build games now, and not shipping all of that high detail content with the product as well. We've got 14,000 skins, I think, in Fortnite. It's crazy. And we ship every single one of those cosmetic textures at highest resolution on most of our major platforms. We did some work a bit earlier in the year to stream some of that high-res data on PC and Android. But Switch has suddenly become one of those platforms where we're close to running out of being able to give Fortnite to our players on Gen 1 Switches. And it cuts out a huge amount of the market. So we've introduced essentially what we're calling IAS, individual asset streaming, but you can think of it more as runtime virtual assets. Same process. It's very Zen-like. What we have on our disk, what we ship in our cooked data, is a bunch of structured data and then some references to bulk data. And like we did with the game feature plugins, we upload that stuff, all of the high-res data to CDN, and then stream it on demand to the platform as and when you need it. So obviously one of the guiding principles of this is that streaming anything from live cannot result in a lower quality or impact gameplay in any way, and the overall quality of the product. And it's very easy to just say, take all that data, put it up on the network, and then pull it down. But it does require you to kind of think about what kind of data that you would stream and what your graceful failure conditions are and so on. And it's a different methodology. It's similar, I guess, to regular texture streaming. Not only is it textures, like virtual assets, we've applied this to a bunch of other types as well. So we're able to stream static meshes, skeletal meshes, audio. So all of these types are things that typically swell up your initial install, and players either can live without, or they can pre-download or whatever. So again, giving players a choice about how much they download, how quickly we can get engaged with the products, how quick, and again, even just taking all of the large textures out. I think we lifted something like 8 gigs worth of textures out of Fortnite and put them in the cloud. So our builds are 8 gigs on Switch, 8 gigs smaller than they would have been. And not only that, it gives you smaller packages, right? So it solves a lot of the problems. So anyway, I think that's the last slide.
I believe so, yeah.
So we're a little bit, we've done it in 5 minutes less than we expected to, Daniel.
More time for questions, but before we jump into Q&A, maybe just a show of hands in the room. Who's used virtual assets? Okay. Who's used the cloud DDC? Okay, you're gonna get more hands up next year, I hope. So.
Who would like to use virtual assets? Ah, nice. And who would like to use the cloud DDC? Okay. So, awesome. I mean, we're here tomorrow. Like, each of the teams we know have got a different makeup. You know, some of you guys have got cloud engineers, and I know some of the teams that we've worked with to get Unreal Cloud DDC working have dedicated cloud engineers, and that's not, you know, not what every team.
the show. 3, get ready. 4, 3, 2, let's go, 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 go. On your mark, get ready, set, go, 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 go. On that jump, that get up and go, 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 go. On your mark, you ready, yeah, go.
Oh, yes.
No, that's good. It will be a nice session. Did you enjoy the sessions previously?
Yeah.
You went to good ones?
Yeah.
Yeah, you've been good.
All right, thanks, Danny.
I think he's a fan. Not sure I understood the sign.
No.
Hi, everyone. Can you hear me okay? Good. Well, thank you. Thank you very much for joining us. It's one of the many tracks that we have in these sessions these days, and I'm really, really happy here to be joined by Eddie and by Lee to present this fantastic and out from this world presentation. We'll have a very, very good session here, and because a room is always very cold at the very beginning, maybe we can just welcome them correctly. So Eddie and Lee.
Okay, thanks. Thanks, Seb. Thanks for inviting us. So again, my name's Eddie Paddock with NASA at the Johnson Space Center, Houston, Texas. Yeah. Go Astros, right? So anyway, Lee and I are here to talk about how NASA is using simulations and game engine technology to get us back to the moon. So I'm the VR lead as part of the Software, Robotics, and Simulation Division. That's under the Engineering Directorate at the Johnson Space Center, and specifically in the simulation and graphics branch, where we develop applications supporting training and analysis in support of both station and the new Artemis mission. And Lee Bingham, colleague on my left here, he's part of our team in the simulation graphics branch, who's kind of our top-notch lead of developing these applications that we're gonna go over here. So anyway, with that, let me go ahead and get to it. Agenda, we're going to just do a split agenda, about 20 minutes apiece, where I'm going to give kind of a higher overview of us going back to the moon and a little bit about what Apollo did and some of the manned and unmanned missions we're going to do and talk about the visualization and simulation training facilities at kind of a high level, and then Lee's going to dig into some of the technical visualization applications, using Unreal 5. Again, about 20 minutes apiece. So NASA's going back to the moon, but this time we're going to the South Pole, right? So we had 6 missions during Apollo, the last one being 1972, where the picture on the right is actually Jack Schmitt, Apollo 17 astronaut. So it's been, over 50 years. But this is a little different. We're going to the South Pole. As you can see, the other Apollo missions were all close to the equator, where they had ideal lighting conditions and well-known terrain to land and explore. It's not the case in the South Pole. So Artemis 3, which is tentatively scheduled November of 2025, or Artemis 2 is going to be a year from November. So Artemis 2 is the first manned mission. They're not going to land, but they're going to get in that near rectilinear orbit of the South Pole and kind of do a dry run without landing. And then Artemis 3, we're going to, with the help of, right now, it's SpaceX and the Starship, it's going to ferry us to the moon. Orion is the vehicle that brings astronauts on the Space Launch System rocket. So the conditions in the South Pole are different, and they require a lot of early planning, analysis, and training. Oops, going the wrong direction. Okay, so this is actually the picture is using Unreal 5 of the South Pole along Connecting Ridge, and I'll be going over some of the landing sites. But you can see the sun's at a very low angle, plus there's no atmosphere, it's real bright. You can't traverse looking towards the sun without proper shields and, kind of tacking back and forth, because the moon is on about a 1.5 degree axis. So, the poles are almost vertical, so the sun is rotating around the horizon, and it's always, at best, 1.5 degree at the pole, and at worst 1.5 degree below, completely shaded. And then when you deal with all the terrain and the mountains blocking, you have all these shaded areas and some permanently shaded areas. So that's why we're going back to the moon to find water ice. We've done some probes, NASA has in other countries, and detected with spectrometers that there is hydrogen and oxygen in the form of water ice. So that's why we're going there. Obviously, with water is a valuable resource. You can have air, water, you can get fuel from the hydrogen. So that's why we're going back there. That's why we're risking going to these harsh environments to find water ice. So that's why these simulations and visualization tools like Unreal can help us create that virtual world, and we can set up the ephemeris and the planets, get the right lighting conditions, use real digital elevation maps. So another comment there is about the cycle of a day on the moon is 29.5 days. So it takes, that's like the cycle of the phases of the moon. So it's like one lunar cycle is 29.5 days. So then we can simulate all that and set up a particular time, location, and know exactly what the terrain looks like, at least with the resolution of data we have. This is a kind of a map of the 13 Artemis regions that are being considered. These are all under the 84 south latitude. That's the outer circle, if you can see that. The inner circle is 87, with 90 being right on the South Pole, where Shackleton Crater, and most of you probably heard about that. That's as big as the 610 loop in Houston and 4 times as deep as the Grand Canyon. It's not that steep, but it's a big crater. But you can see there are bigger ones around it. So the areas we're looking at right now, studying intensively, is Connecting Ridge, which is right to the right of Shackleton Crater. And another area of interest is the Nobile Rim, and that's where Viper is going to land, which I'm going to talk about in another slide. Viper is a NASA rover that's going to land, hopefully it stays on schedule, a year from November, and that has some instruments and a drill to basically verify that there is water ice there. So that's just a picture of Viper, which is Volatiles Investigating Polar Exploration Rover. NASA loves acronyms. But yeah, that's the plan on going to that crater. This here is actually one of the first Unreal 5 apps we built last summer. A lot of the team that are here in the front row helped out with this, of the Nobile site in Unreal, using the 1 meter shape from shading data that they don't have everywhere, but they have it here. And then we upscaled that with 20 centimeter data to distribute rocks and smaller craters. And what we're looking for here is the bounce lighting effect that you can see there reflecting from the suit, where our other renders can't do in real time. We can't do bounce reflective lighting or nanite or a lot of other things that Unreal can do for you. So this along with the double precision part of Unreal 5 really got us going towards using Unreal. And before that, we've been doing visualization and graphics in VR since the 1990s, building our own OpenGL-based renderers. And so we're still using some of those today, but Unreal is the first commercial renderer that can do the job for us. So some of the specifics of the visualization and simulation software we're building up. Again, this is, right now we're doing early analysis, risk reduction, planning, but these same tools will be used for training once we get a specific site and what tools we're going to use, and so we can lay out that training plan for the astronauts, for EVAs and for landers and for rovers. Rovers aren't going to be there till Artemis 5 and 6. So Artemis 3 and 4 will be just surface EVA. EVA is extravehicular activity, a spacewalk. So a spacewalk on the moon. So we're building up desktop tools, and Leo talked more about Dust, which is D-less Unreal simulation tool, and that's kind of our flagship Unreal tool that can render all of this lunar terrain and mix in traverses and set up ephemeris data for correct date, and lighting conditions, so we can use that for desktop analysis or hook it up to a simulation and articulate the data. So most of our high-def sims are built in a tool named Trick, which is on the bottom there, which is it's basically a toolkit, a simulation toolkit or architecture tool that's C++ based that has auto code generation and it sets up all your input-output. You can do real-time scheduling or event scheduling. So basically all your high-fidelity math models and dynamic subsystems, flight software, can be modeled in real time, and then you pump that data of anything that's moving to Unreal, and you get your real-time human-in-the-loop sim, which we've got for landers, for rovers, and you'll see some of these in the videos. Again, we're using Unreal 5 for that. Unreal 5's important capabilities. I mentioned the double precision, because we use planetary data and sims for center of the Earth, center of the moon, or solar system, where if you don't have double precision, you have values jumping all over the place when you're trying to drive it with a double precision sim, when you're trying to drive the graphics. So lighting conditions and lighting reflection and the bounce lighting and the Nanite, real-time performance, those are other big benefits we get that most of you know about. The LRO, that's the Lunar Reconnaissance Orbiter, that has all the data out there for our elevation maps, and that's on a public website, Goddard. It's on the PGDA. That's a Planetary Geospatial Data Archive, where we get this data in GeoTIFF format. And with Unreal, we've developed some tools, again, that Leo will talk about, some clip map tools, and that add curvature to this flat geospatial data and create a 3D model of the surface. So you have all the right shadowing and reflections from the sun. And we've also upscaled the data. I mean, most of the data is 5 meters on the 84 South, and that's not enough detail to show the craters and the rocks we know are there. So we worked with the science community at NASA and did a random distribution of craters with the right diameter to depth ratio, and scattered the rocks where we think they're at. But we still have some more work to do in that area. Multiplayer VR and state management, obviously we take advantage of that, especially in our VR software. We have 2 astronauts, EVA, the camera on their shoulder, piping that Unreal camera video down to the MCC, so that and the astronauts are holding navigation maps and traversing. We're already simulating all of that in kind of a full-up MCC, EVA, lander, rover scenario. And N-Display was real helpful with replacing our current visualization software. It had a real nice syncing mechanism to support dome projection systems or video walls, where you have like 5 or 6 machines driving a video wall where it all has to be synced, so there's no tearing. But N-Display helped us basically plug Unreal right into, and then we got the benefits of all the other Unreal capabilities. So just back to the kind of the applications we're building that these relate directly to the videos I'm going to show you next. It's desktop trainers, like the Dust tool. We have video walls and projection systems. The virtual reality for EVAs on the surface. And then we're just starting to use Vario XR3 headset to do a mixed reality environment. So we have desktop trainers and even motion base and video wall, and some of them with VR, but we don't have that pass through where you can see your hands and the hand control or your displays, but then everything else is virtual. And the Vario headset looks very promising. We're having some performance issues with it just because we plug our current scenes that we run on a Vive into it, and when you do that and you bring in the cameras and other things, you just have to tweak it to make it run real time. We're not there yet, and plus we need to learn all the Unreal's ins and outs with the Vario. We haven't, but I do have a little prototype video of that. So this next video is of in the SEAL, which is our kind of desktop lander sim that we now have a NASA reference lander, but we can also do Starship and other landers. Kind of a desktop trainer where you can land on the moon, go to your trajectories and land at the spot of intention. And This is actually not Unreal in the background there. It's our DUG, which is our Dynamic Onboard Ubiquitous Graphics, another acronym. But that's the tool that we're kind of, on our new projects, we're kind of using Unreal to replace it in a lot of ways, especially for Artemis. But anyway, you get the idea where you have your GNC controls and displays, and those come up on the monitors inside the vehicle. This, wrong direction. This is actually Unreal. So this is what we're working on integrating into that environment. So this is kind of a bird's eye view, but there are camera views that are real similar to this, that show this. So you can see there it's flying towards Shackleton Crater, the big crater up at the top. Those series of craters there are called Bear Paw, and then that handlebar ridge there is all connecting ridge. So that's kind of like the ideal spot that has the best light and conditions season round, but better in the summer of the South Pole, which would be the winter of the North Pole. But anyway, this let's just run just a little bit. You can see we're moving the camera around here just to show the fidelity. But underneath there, that's 5-meter data in most places. Some of it goes out. There's like a level of detail like 100-meter data. But when it gets close, it'll use 5-meter and maybe even some 20-centimeter upscale data. The magenta overlays there, as they call that, the doghouse, and that's like the future target, and then the X is like the velocity vector target. So that helps when they're flying manually to line those up to land in the spot you want to land. Again, we're moving the camera around there, but in the real trainer, it would be fixed. Anyway, I'll let it go till you see some plume dust and then those circles there are like the targets for the wheels. So, all right, believe me, it's going to land okay. So this one is, I mentioned the video wall. So there's Lee driving our video wall, which is this is Unreal 5. And it's connecting ridge, and that's just a NASA reference lander. We can also put the Starship there. But this is 20-centimeter upscale data, but at the 5-meter resolution, it is, correct from the digital elevation maps. So there's 5 computers, 2 graphics pipes per computer synced with in-display. And we've also, what Lee will show you is the same application on a motion base, a 6-DoF motion base in VR. So you can see this actually can make some people like myself sick. But the motion base helps it a little bit because it has a table washout and it's synced to the motions, but even that makes me sick. Me, but not everybody. I know, being a VR lead, I shouldn't get sick, but I do. All right, the next slide. This is actually Harrison Schmitt, or Jack Schmitt from Apollo 17. You saw in that picture from Apollo 17 on the moon. So he came last summer and helped us evaluate our systems and gave us some great comments. And this was before we had the kind of bounce lighting into effect on Unreal. And one of the first things he said is, these craters are too dark. You should see some more illumination from reflections from the suit and the rover. And so since then we've got that fixed. And there's a few other things that the Apollo astronauts said. There's another, Charlie Duke also came, and Lee has a picture of him in his slide. And he immediately said, you can't, we had all these rocks scattered. He goes, you can't see the rocks. He goes, they're there, but you don't see them because they're covered with regolith. So we need to take care of that and not just sit them on top of the surface where you see a rock. Only the bigger boulders are like that. But that was just some of the comments. So VR, I mentioned VR, and Lee has kind of the money shot video at the end of our pitch of VR. But this is a couple of our labs, the SES and the PIT, our Prototype Immersive Technology Lab, where we have OptiTrack and lighthouses set up on the truss and TV displays, and we have all the flavors of headsets in there that we can do kind of research and development. And then the systems engineering simulators on the left, and that's actually Might be crew members. If it's not crew, it's some other flight operations people going through traverses on the south pole of the moon. So here's just a snapshot of dust, that DLIS Unreal Simulation tool showing after the traverse. So the astronauts basically did a 2-hour traverse traveling like 2 kilometers to going towards destination craters that they have on their VR maps. Talking to MCC, guiding them through, because right now that's kind of the plan, so we could rehearse that in VR with Unreal. And this is that last kind of mixed reality demonstration with the Vario that Katie did for us. And actually, it's probably about a year ago or longer that we're working on getting this into Unreal. So, but you can see the cutout there, and you can see really good with those Vario headsets, and then it has depth sensors to check your hands, and you got to fix some of that cloaking around the fingers and stuff. But again, this was just the initial prototype a couple years ago. But what's cool about it, I'm just sitting there at the table, and again, the sim's feeding the lander, and that's not quite running real time, but I can get up from my chair and walk to the back of the lander and look out the window, all in the virtual environment, but that cutout is the camera pass-through. And I think this is the last slide from me, and Lee's gonna take it over.
So thank you, Eddie. So I'd like to go into a little more detail on the types of tools and capabilities that we at NASA, Johnson Space Center, engineering, the software, robotics, and simulation division, and even more specifically, the simulation and graphics branch, ER7, of which Eddie and I are both a part of, have developed using Unreal Engine 5 to support things like site inspection, mission planning, analysis, simulation studies for things like lighting and navigation, and eventually to support training crew for various aspects of a mission. So some of you may recognize the next few charts from a presentation that Jack Kincaid and I gave last year at the same venue over NASA lunar terrain. But first, we have a data product, Digital Lunar Exploration Sites, DLES, which is a collection of digital elevation models, DEMS, that have been generated out of instrumentation on board the Lunar Reconnaissance Orbiter, LRO, that represents the truth data to the areas of interest and exploration around the lunar South Pole. From this aggregated data set, we've generated polygonal output products that can be used for sim, as well as ingested in tools like Unreal. Additionally, we have the Persistent Object Database, PODB. This contains things like model reference, location, orientation, and scale of various elements that we've crafted at specific sites, like crater distributions, rock distributions, tools, or surface assets like a rover or habitat. And this ensures that we have a consistent environment across all of our tool sets. So this first video demonstrates our primary capability that we use to generate our terrain. It is a clip mapping method that consists of a mesh with and grids the decrease in resolution by a factor of 2. As the camera actor moves, the mesh follows, and then we update all the vertices with the appropriate displacement and apply curvature relative to the reference ellipsoid, in this case, for the moon. This next video not only demonstrates our terrain rendering capabilities, but also a lot of the environmental effects that we have modeled. For example, the sun is at its full orbital lux luminance value, and we apply an opposition surge effect that is a result of the zero phase angle of the sun and the reflective properties of the lunar regolith. We also take advantage of several of the features of Unreal Engine 5, like large world coordinates and double precision, which allow us to render and position all of our planetary bodies to scale. And our Earth, Sun, Moon geometry is accurate for any date and time. Virtual shadow maps and Lumen allow us to more accurately represent the environment. And we also use Nanite to increase the fidelity by having a lot more geometry in our scenes. And you can kind of see that here with how much of the moon that we actually render in real time. I'll let it pan out here. So please excuse the acronym soup you're about to witness throughout these next few slides, but these are our primary tools and capabilities. I'll kind of briefly go through them, but we've kind of condensed them into mostly plugins so that they're transportable across different projects so we don't have to recreate and re-implement these capabilities in every new project or thing that we're working on. So like I mentioned, the clip map, we have Cut, Clip Map Unreal Terrain plugin that allows us to read directly from the digital elevation model files and modify our clip map and generate our terrain. Tuck, which is cut backwards, is our trick Unreal connector. And that provides us the interface to pull states of our vehicle and system simulations out of Trick and pair those with elements and assets in Unreal, and we can drive all those elements in real time. Our site crafting plugin, SCP, allows us to craft sites like using rock distributions and crater distributions, all in a deterministic way, so it's very repeatable. And then we also have the ability to import and modify and reorient models using that plugin, all running real time and in the built application. Our UE5 pixel restreamer takes advantage of Unreal's pixel stream capability where we capture the render buffer, convert it to an MJPEG stream, and pipe that over the web interface to our displays and controls application, or DC app, and we use that for things like camera views. Loot is just a headless tool that allows us to have a little interface to export our clip map. We can configure whatever size and location and export that as a polygonal model is in the Wavefront OBJ format. Our GAS is the graphical astrodynamics simulator. This is a plugin that allows us to natively build our own orbital dynamic simulations in Unreal. It supports both ephemeris propagated and integrator propagated spacecraft simulations, as well as spherical and geopotential gravitational force models. And not to be self-serving, but the LEE project, the Lunar Exploration Example Project, is a project that we've kind of pre-compiled a lot of the capability in our plugins and provide a scene and everything that you need to start with a lunar environment with the terrain, the sun, moon, earth ephemeris, a simulation connection, and the models necessary to build your own sim. We've distributed this to various partners across NASA, and just requires a software usage agreement. So this is kind of a little demo reel of the GAS tool. We're driving the International Space Station. Here, it can either be through ephemeris, or we can do an elliptical orbit, and it shows kind of nighttime, daytime as it orbits around the Earth. Here is Gateway in its orbit around various planetary bodies. This one is the Moon. For some reason, Jupiter.
So we could do it.
Or Saturn. But we have all these nice models of the planetary bodies. We also track the solar panels to the sun. So as the ISS goes through its orbit, all the solar panels track to the sun. So as Eddie mentioned, the Digital Lunar Exploration Sites Unreal Simulation Tool, a lot of words, DUST, is our flagship tool. It's originally conceived to provide a way to visualize the lighting conditions at the lunar South Pole for any date and time at the 10,000 meter view or at surface level, but has since evolved to provide a lot of capabilities for simulation, visualization, analysis, all using this high fidelity digital model of the moon. One thing to note is we do have a public releasable generic version that will soon be available on the NASA's software catalog, available at the link. And I'll go through a couple of these capabilities that are in DUST. Spice integration is our JPL-derived ephemeris toolkit that allows us to have the appropriate sun, earth, moon positions and orientation based off date and time. Trick integration, as I mentioned, is how we get simulation, high fidelity simulation data to our graphics systems. And our PoDB integration allows us to have a RESTful API to query our database and pull information out of there for various assets that we've crafted at sites. Some of the more visually appealing ones, the rover and EVA traverse capability allows us to plot or import traverses for EVA or rover traverses in either a JSON or GeoJSON format, and allows us to visualize that on the lunar surface. They're modifiable in real time and can be re-exported to be ingested in other tools. Our communication line of sight visualizer provides kind of a heat map. You can place a comm tower with infinite power or some sort of an attenuation. You can view its LOS heat map there. We also have gateway and earth LOS visible in that comm visualizer. Our topography capability allows us to have a elevation map or a slope map, and with the appropriate contour lines, and all this is done through shaders and applied to the surface on the moon. And then what tool doesn't have a measuring tool, so we are able to place little nodes and measure them all in meters. So this is kind of a highlight of some of those features I just mentioned in DUST. Obviously, this is faster than real time. This is the measuring tool, all sped up. But next one, I think, is the topography visualizer. Here's the elevation map with contour lines. There's the slope map. This is our comm heat map. So we place a comm tower. There's one with attenuation. We can also place multiple ones to have links between comm line of sight. This is the EVA traverse, so plotting points just at random at this point. But then we can visualize that, and then we can actually watch our little astronaut guy hike across our newly plotted traverse. And it follows the elevation in the terrain. Our site crafting plugin allows us to craft all these craters and rocks, and they're all deterministic functions that we use to allow us to have repeatability. And this just demonstrates some of the model imports that we took, in this case, this HAB model, and we can scale it, reorient it, reposition it, and have it anywhere in our scene. So as Eddie mentioned, using the end-display capability, another acronym, MUD, Multi-Unreal Displays, we're just leveraging end-display, and we're using this capability for our human-in-the-loop studies. So here we're driving a rover on the lunar surface. We have our displays and controls application, displays for crew input. We have a hand controller for them to be able to pilot the vehicle. This is our simulated mission control center. It's up in the mezzanine of that same area, the systems engineering simulator. We use the pixel restreamer capability to provide camera views. So like in that large television above the MCC, we are providing a masked camera view from a rover. So Eddie mentioned Jack Schmidt, and here's a picture of me with astronaut Charlie Duke. So they provided us crucial information from firsthand experience of being on the moon that fed back into refinement and increasing the fidelity of all our simulations and visualization products. And it's great to have that input from someone who's actually seen it firsthand. So Eddie mentioned the motion-based simulator, the thing that makes him sick. So this is a high-performance 6 degree of freedom Stewart table. It does have an 1,100 kilogram payload with a 1 millimeter repeatability and accuracy with that payload. We've internally developed the washout motion program that provides all the motion cueing and vehicle attitude driven from our trick simulation. Currently, we're using VR to render our scene using, not wireless, we're actually using a wired HTC Vive Pro 2, and we have a Vive tracker mounted to the table that backs out all the table motion from your VR perspective. So you're not adding additional motion in your scene. So this is a video of our motion simulator in action. We performed a preliminary handling qualities study with this. And so we have a test subject. They perform a little bit of a FAM section, familiarization session, where they get used to the controls, the motion of the table, the response of the vehicle, and then eventually we set them on a traverse, and they can determine whether they follow exactly that traverse, drive through all the craters and all the bumps, or perhaps drive around them to avoid all the bumps and responses that the vehicle would have for craters and rocks and things of that sort. And so they follow this traverse for a good period of time. We've also implemented a display that provides them a map, some telemetry, so their current velocity, what drive mode they're in, and whether their brake is engaged. So sometimes it can be a pretty wild ride. And then finally, Inverse, which is our NASA's virtual exploration rendered simulation environment. This is kind of our accumulation of all of our capability for graphics and simulation into a singular product. This allows us to provide a deployable application across all of our facilities. So whether it uses VR, in-display for a video wall, for domes and projectors, desktop clients and camera views, the motion-based simulator, or even like the lander simulation facility, the Simulation Exploration Analysis Lab, or SEAL. And this kind of allows us to have a unified environment where we can tie all the states. We can have person in VR, we can have someone landing at in the lander or driving the rover, and all of it is visible in a single application. And so this is kind of like that highlight. We have 2 crew persons coming down an elevator and Starship. One of them is quite a bit taller than the other.
Must be me.
So here's a tool sample. We're collecting rock samples from the surface, placing them in a sample collection bag. We can take this bag, stow it on our vehicle, and put it on the rover. This is a person, we're kind of showing some of the bounce lining effects from the radiators on the hab. We've modeled a camera, so crew can actually take in-sim pictures of things that they find of interest, or as they're taking, he wasn't jumping, I promise. And then this is kind of when the sun is below the horizon, showing the suit lights and operating in that environment. This is, we model how quickly they can traverse up and down slopes based off of Apollo data. They can pick up any of the rocks. They can turn on their suit lights, and all the capability that is in Dust, where all the trick integration, the visualization capabilities, the slope maps, and all of that are integrated into this tool as well. And then one of our developers decided to shoot a kind of somewhat dramatic scene here with the desktop camera is behind the crew person. So that's all I've got for you.
Yeah, we just wanted to give a few acknowledgments from the programs that that give us funding and requirements. NASA's Exploration Systems Development and Mission Directorate. There's 2 offices and programs under there: EHP, which is EVA, Human and Surface Mobility Program, and Moon to Mars Strategy and Architecture Office. So they're the ones that those programs and offices are giving us requirements and funding to develop these tools in support of early analysis and future training. And then I have our JSC Engineering, Simulation, and Graphics branch. Again, that's in the Engineering Directorate. That's under the Software, Robotics, and Simulation Division. And the labs, and so we have some of the team members here. We have the IGOL, the Nexus, the PIT, VRL. So it's a team of around 20 people, and our JSC contractor teams. Lee and I are civil servants, but we have a lot of great contractors from CACI, Cyford, Jacobs, and Medics. So just wanted to give them some acknowledgement there. But that is it. All right. So we do have some time.